A very good morning to one and all present here. I, Dr. Doel Bhattacharya, Assistant Professor of the Department of Chemistry, Dada Ramchand, Bakhru, Sindhu Mahavidyalaya, welcome you all to the second day of the technical session, ICNHTCS-2022. We have with us our chairperson for the session, Dr. Atul Wankhede sir from VNIT, which is my alma mater as well. And we also have with our eminent speaker, Dr. Kiran Tari sir. He's from VIT Chennai. Sir, welcome you, both of you.
Thank you, madam.
Sir, you may please put on the video. Kiran sir and Atul sir.
Yeah.
Yeah, thank you, Doel madam.
Great to see you both after such a long time.
Yeah,
all
that's
the
what
memories come alive. Okay, so let us start with the formal proceedings of the session. So I take the opportunity and the honor of introducing our chairperson for today's session, Dr. Atul V. Wankhede sir, who has been my mentor, who has been my inspiration as well. So let us talk, like the words are very short, but the content is more. So I have to just put down something in very short, sir, in your honor. So Dr. Atul V. Wankhede sir is serving as an assistant professor in the Department of Chemistry of Visvesvaraya National Institute of Technology, Nagpur, famously known as VNIT Nagpur. And his research interest includes nanomaterial synthesis, green chemistry by photocatalysis, nanocatalysis for organic transformations, nanomaterials for energy and environment, nanomaterials for photocatalytic water splitting. Sir has his research objectives, which includes to develop a novel nanomaterial and to scan them for UV visible light responsive photocatalytic activity for the degradation of emerging organic pollutants using simulated wastewater containing organic azo dyes, methylene blue and methyl orange. He wants to introduce an innovative and sustainable technology for wastewater treatment processes by employing the efficiency of these nanomaterial as catalyst or photocatalyst. He also wants to develop a sustainable nanomaterial for photocatalytic water splitting under UV visible irradiation. Sir has, to his credit, published more than 30 research papers in SCI Scopus journals. And I'm glad that I'm a part of his work. And he has guided more than 2 PhD students, and already there are 6 PhD students ongoing under his guidance. He has also served as the principal investigator of sponsored research projects. The first is the UGC minor research project on the synthesis and application of benzoprown ether, derivatives of dithiocarbonate and dithiazolidine for the extraction of univalent and bivalent metal cations. He has visited the King Abdullah University of Science and Technology, Saudi Arabia, for the sponsored project by COS to work on development of titania and zinc oxide nanocatalyst in 2012. Then he also has backed the sponsored project under the DAE BRNS, which was of 38 lakhs. And recently, Sir is already serving as the principal investigator in the ongoing DST sponsored project of 1.5 crores. Sir has a vast teaching experience of 18 years. He is also involved in consultancy testing, and he is a member of many professional bodies. Sir, we are very glad to have you today with us on this platform.
Thank you.
Please accept our invitation. And I would now hand over the formal proceedings of introducing our guest speaker for today to Wankhede sir. Sir, please take over the session.
Thanks, Dr. Doel, for offering this position of a session chair for this Elite conference, right? Firstly, I will like to thank the organizer, and I will like to welcome the today's speaker, Kiran Kumar Tadi, Dr. Kiran Kumar Tadi. it's a triangle. Doyle is also from our institute, and it's fortunate that I am hosting my own students, introducing my own student as a speaker. So Kiran Kumar Tadi, I know him from when he has joined a VNIT in 2000, I guess around 9 or 10, right?
Right? 10, sir, 10.
10, okay, yeah. So it was a nice time spending. I know him from, he was a really hard worker researcher, and that has been reflected after this many years. You can see that when we are calling our own students as a speaker, the guest speaker, that means the hard work has been reflected. Talking about Kiran Kumar Tadi, he is now working as an assistant professor at the Center of Healthcare Advancement and Innovative and Research at VIT. Done his PhD degree obtained from VNIT. Then a postdoc, the postdoc, he has gone through an exhausted postdoc from 16 to 19 at TIFR Hyderabad Center, and then joined under a fellowship. He had joined an Hebrew University as a postdoc fellow, where he worked for 2 long years on peptide-based sensors and self-assembled monolayer materials. Now, about his professional experience, he has a professional experience. He has worked as a teaching assistant at VNIT and both the postdoc at a very good institutes, one at TIFR Hyderabad, another at Hebrew University, Jerusalem. And now currently is working at VIT, which is also a renowned institute in India. He has several awards to his credit. The Arsken postdoctorate fellowship, through which he went to an Hebrew University, one of the renowned universities of Israel. Then he has been awarded with a Chemosphere Travel Award in 2017, a Best Paper Award in International Symposium for Research Scholar organized by IIT Madras. Then he has also achieved a first prize for Best Poster Presentation in International Discussion on Meat on Electrochemistry and its Application in 2014 at Amritsar, Punjab. During his graduation and post-graduation days, he has stood in a merit list and was a topper in both his master's and his graduation degrees. He has experimental skill lies in the preparation of self-assembled monolayer biomimetic polymer, modification of electrodes and their electroanalytical characterization, fabrication of microfluidic channels integrated with the microelectrode system. And he is also involved in the preparation of the graphene and metal dichalcogenides, which are very difficult to synthesize, as I know that, using a solothermal and vapor deposition techniques. And of course, he is usually very good in characterization of a nanomaterial and characterization of polymer. His research interest lies in the development of two-dimensional nanomaterials, development of chemical sensors, microfluidic materials. That electrocatalysis is one field where he has started working from, and he's also very good in computational studies, computational modeling of the compounds. Apart from this, he has handled several instruments and has got 30 plus research papers in a very good, those are SCI or Scopus journal, very good journals. He has been, he has a reputation of publishing the papers in a very good journals. Along with that, he has 2 book chapters to his credit and has participated in several national and international conferences. And to his, he is also a reviewer and a member of various reputed journals like American Chemical Society. And he is also a life member and annual members of several bodies in India as well as at an international platform. So I welcome you, Dr. Kiran Kumar Tadi, for this session. And now I will hand over the platform to Dr. Kiran Kumar Tadi, and we will all will enjoying the excellent exhaustive talk by Dr. Kiran Kumar Tadi. So welcome.
Thank you, sir. Thanks a lot. Actually, it is so exhaustive, that one you told, but not required. Actually, we are all, you know, if a person did his PhD in some institute, he is emotionally attached. I don't know how much far he attached to his school, but definitely one person wherever he did the PhD, definitely he attaches to that community. It's really nice to see you all in this platform. There is a lot of things to achieve, but still, okay, sir told a lot of things about me. Okay, not that much. Thank you, sir. Thanks a lot for your kindful presence here and give the introduction about me. And I am also thankful to the Doyle Bhattacharya, Dr. Doyle Bhattacharya, for inviting me for the as a one of the speakers here, and also the coordinators who are all arranging here, the Sarkar ma'am and Mandagani ma'am and other Sunil sir. So I am highly privileged to be here as a one of the speakers. Thank you, sir. Thanks a lot for your introduction, and it's really nice to meet you after a long time.
That's
So, sir, one of the thing that I would like to see, sir, is so young and dynamic, always. So we should learn from him a lot, and that I like that one. Okay, thank you, sir.
thank you, Kiran.
Okay. Yeah. Can I start the session?
Yeah, you can.
I mean,
Please proceed.
yeah. Yeah, is my screen visible?
Yes, sir, the screen is visible completely.
Yeah.
Please proceed.
Yeah, I hope the participants mostly are PhDs or postdoc background, so that I will give the some fundamental background also during my talk. So I hope that's fine for you.
Yes, sir. Yes,
So
sir.
instead
Completely.
of going to the deep details of that. So today I would like to give my some research topic on the how can we make the intrinsic properties of the two-dimensional nanomaterials for the biosensors making and fabrication. Of course, you don't know about my introductions, sir has already given. So these are my affiliations. Actually, the problem of this origin starts from the main problem is the population, increasing the population. So if you see the Sensex from the 1990 to 2015 and the projected ones, if you see, it is steeply increasing a lot. And unfortunately, this is more in the from the India, so which is covering 135, 26% of the this Sensex is from the India itself. It is showing. So because of the this world population, steep world population, what's happening? The sustainability is a question of matter. So obviously, this sustainability involves in the three factors. So one is health and energy and environment. So when this population is so rapidly increasing, so then the sustainability which is entangled with health, energy, and environment, definitely it is a question of matter. So we have to think about this one. It is a serious matter of thinking. So in this case, so as my talk mainly focuses on the health here, and a glimpse of the energy on the energy also, sustainable energy also, I will give you a flavor of green technology which produces the some energy here. So these two are the main important factors that I would like to focus here. So if you see here, the when you are considering nowadays situation, you can see what happened. So 2.5 years we are completely isolated. So we didn't come out, and so there is nowhere the people are really afraid to come outside. And whatever you see here, the 1 million deaths, so it is more than that one. So more than the 1 million deaths are so far because of the pandemic situation. So in this case, so what is the main important factor to avoid this spreading of this COVID-19 from the one person to other person? Not only this one. So any type of the so spreading disease. So what is the main factor? So actually, we don't have the correct diagnosis at the molecular level. So if you are able to detect that one, yes, these symptoms of the COVID is due to the only because of the COVID, or because of the some other factors like TB or some other influenza or anything. So or just like normal seasonal cough and cold. So nowadays we are in the situation that one, even if we are getting a cough and cold, is it because of the COVID-19? So we are scared of that one, because the main thing is we don't have the diagnosis in a proper way. So here the diagnosis or therapeutic should be the at the molecular level, and it should be the preventive and earliest recognition. So it should not come like a cancer, where the cancer, if you see the cancer also, so after the third stage or second stage, you are able to detect. But at the earliest stage, we are not able to detect here, because the diagnosis that we are speaking about when you are going for any doctor, and if you are talking about telling that one as a some symptoms, if you are telling, so actually the molecular diagnosis or clinical test should be a exact way that one, so where he exactly find out the reason for the these symptoms. So whether it is a COVID-19 or some other seasonal fever and cold, so he should be in that case. And as in the case of the India, if you see, so it should be the cost effective also. So it should not be so far from that one. So for example, if you see the RT-PCR test, so now the hospitals are charging around 1,000, but when the COVID-19 came, so they are even charging the 3,000 also they are charging. So it should be the cost effective and point of care. You should not go around the hospitals and all, because you know that in India, so we have the many rural areas where the health centers are not reachable. These clinical tests and everything are not reachable. So the main problem here that we are facing is the diagnosis of this corona or COVID-19 effect is we are not able to diagnose correctly whether it is from the COVID-19 or something else. So if it is correct, so then obviously we can stop the chain. I mean to say, spreading from the one person to the other person, we can easily stop here. So in this case, you have the many diagnosis techniques. However, the biosensor plays an important role here. So because if you see the biosensors, they are simple and fast, and they are highly selective. So n number of the your genes, so exactly your disease causing gene can be detected, and they are highly simple and fast. So for example, if you are going to the any Apollo diagnostics, and if you are giving any sample for the glucose levels, or whether the diabetic or anything, so if you would like to know, so if you give the morning and evening, he will give you the report. Of course, he is sending through the mobiles, through the mails, and he is going to send. But this much gap is not is very large for the when it comes to the health crisis in fact. So it should be very fast. So for example, nowadays you can see the glucometers, where you can see you are sitting in at your home, and you are just taking a drop of blood, and when you are putting on a glucometer, so immediately it tells you that one how much glucose levels are there in your direct whole blood. It is going to tell you. So it is highly miniaturized. You can see that a glucometer is just like a pocket size meter if you have. And every time you can wherever you want, you can go here, and there is no kind of the any tedious tedious processing methods are not there. So like sample processing methods are not there. So you can simply you can detect in this case, in the case of the glucose. But to reach this level, how much hard work was done by the scientists? So for example, you can see the glucometer easily, and nowadays everything glucometer is quite really common nowadays having in a home. But to reach this level, they made a lot of research. They did a lot of research publications. Then only it went to the as a product it went. So it is not a simple one day job to get this kind of the product in the market. Okay, so after many years of the research for the glucose detection, so far also now also you can see the glucose level detections at a diagnosis level. Okay, now also you can there are many research papers and patents are also publishing. So recently from the Hyderabad, one of the startup, so what they will do, they will take the IR spectrum of in your body without having any it is invasive technique, no need to take the blood out. And so from the IR spectra, they are able to detect the whether what is the glucose levels in your body. So they are able to detect one of the startup company, because diabetic patients and blood pressure patients are continuously increasing in our India because of the diet conditions and other matters. So in this way, the biosensors, when the biosensor talking about the biosensor, they are and their role is enormous actually. So if you see that one, because of their miniaturization, they are integrated a lab on chip. You don't need to do any kind of any kind of the tedious lab processing and all. So it is not required at all. So you just take one sample of the blood, so you can directly detect whatever you want. So in this way, the biosensors plays an important role in this case. So when it comes to a sensor, so maybe some of the people don't know the because of their interdisciplinary or other factors. And I will give you a small touch on the what is sensor. Sensor is nothing but a device that transforms a physical property to an analytical signal. So mainly, if you see here, there are two types of the two main components are there. One is transducer, and the other one is the receptor here. So here, the receptor that you are choosing here, it selectively recognizes the one element. So for example, you are detecting the glucose here. So, but you have the ascorbic acid, vitamin C, or another some metabolites, other metabolites, epinephrine, and your many metabolites and all is there. Some drugs if you are using, so it contains a lot of drugs also. But your biosensor or your receptor should selectively choose the glucose out of that one. So for example, A, B, C, D are there. So if you are preparing your biosensor or fabricating the biosensor for the D molecule, it should not choose A, B, C. So it should selectively choose the receptor of the D only. So then it should selectively capture that one. And when it is selectively capturing this receptor, so then it is there will be a physical changes occur. It could be a resistance, it could be a conductor, or some kind of the oxidation or reduction, so whatever it may be. And this physical signal, so it will be transferred as a signal by the transducer, because transducer changes this physical parameter and to an electrical signal or any other signal it changes. It depends on the what kind of the sensor are you speaking about. So in this way, the receptor selectively chooses, and whereas the transducer converts this physical changes into a electrical or electronic or optical signal, whatever it may be. So here the receptor is a very important factor when you are fabricating a sensor, because until unless it has highly specific, until unless highly sensitive and selective, so you don't get the reliable result. So nowadays also you can see some of the biosensors that is detecting COVID-19 may show the false positive or false negative they show. So why they are having that one? The receptor is incapable of or not having the right ability to detect the COVID-19 spike protein or any other things. So in this way, the sensor is made up of, and it has two components, main components. One is receptor and the transducer. So you might have seen the many materials for the fabrication of the biosensor, gold nanoparticles, CNTs. CNTs or many. Someone has. You might have seen many materials like gold nanoparticles, graphene, and other things. And CNTs or core shell nanoparticles. Many might have you have seen here. But here, if you see the two-dimensional nanomaterials, why I am focusing here the two-dimensional nanomaterials? And if you see the two-dimensional nanomaterials, the each and every atom is in contact with my receptor. So, for example, if you take here as a two-dimensional nanomaterial, which is like a sheet-like material, am I right? So, just like a sheet of paper, if you are imagining, so the atoms are arranged on the same plane; they are arranged here. So when you have these kind of the material in comparison to the bulk nanomaterials or any other nanoparticles if you see. So for example, let us consider these two here in the case of the bulk nano, some metal nanorods or these two-dimensional nanomaterials if you are considering. So your analyte is glucose here. Glucose is attaching to this one selectively, either oxidizing or reducing here, and here also reducing here. So this is the receptor. Immediately this receptor has your transducer. Can you see Doyle? Someone has. Can you unmute them? Sorry, mute them. Okay. So if you see if you compare these bulk nanomaterials and the two-dimensional nanomaterials, if you see, and let us say that if I'm detecting the glucose here, so glucose, if I'm detecting here also, I am detecting here also. The signal that is coming from the two-dimensional nanomaterial and signal coming from my three-dimensional nanomaterial, if you see, so the signal should transfer to the transducer. Next level is transducer, whatever I have here, and the transducer here also I have the transducer. The signal should transfer to this one. So in this case, when you are choosing a two-dimensional nanomaterial, the signal is directly going to this transducer here. But only the surface molecules are in contact with the glucose molecule, but the signal should travel along with the all three-dimensional here. Then only it should reach to the my transducer here and converts to the analytical signal. So in this way, if you are comparing these two here, so you can find in the case of the two-dimensional nanomaterial, high sensitivity and high selectivity you can find in this case, because there is no loss of the signal during the traveling of this signal here, as well as each and every atom is in the contact with your glucose. So for example, if you see here the glucose, the inside molecule which you are taking here in the three-dimensional nanomaterial, some nanoparticles may not interact with the glucose. So unnecessarily they are here and impeding or resisting my analytical signal that is coming from the glucose. But here, if you see, as it is a sheet-like structure, so each and every molecule is in contact with my glucose molecule here. So that's why two-dimensional nanomaterials are the perfect materials for the for the fabrication of the biosensor. Moreover, you might have listened that if you take this any graphene, so graphene is highly sensitive to the any adsorption process. So the electronic band gap and everything will change. The physiochemical properties changes in this case of these two-dimensional nanomaterials. So in this way, the each and every atom talks to my analyte here. So that if I'm making a small dopant in this case, so it gives you a huge electronic properties and electronic structures modification you will get here. So but the main drawback of this graphene, if you see, it doesn't have any molecule to interact with your specifically interact with your analyte. So graphene is just like a carbon atoms are spaced at a honeycomb lattice structure, you can imagine, where the benzene molecules are attached, fused together for a 5 microns by 5 microns or 10 microns by 10 microns or less than that, if you are going to the smaller sheet size. So but it doesn't have any specific site to interact with a molecule, because for example, if you have the H plus and if you have the OH minus ions, then there is some interaction. Just for an example, as for the PhD students, I am telling that there is a hydrogen bonding or any electrostatic interaction happens here. But this doesn't have the my graphene doesn't have anything here. So that's why we need to make this some modification you need to do in order to interact with my molecule here. So here the example that I'm giving here. So the fluorination of the graphene, how my fluorinated graphene is going to affect the electronic structure and the selectivity of my sensor for the sensing of the ammonia. So if I'm doping this graphene with a fluorination about 5%, it is tremendously acting as one of the nice best receptor for the sensing of the ammonia molecule due to the fluorine and ammonia interactions here. Because as I just told that one, even though the electronic properties of graphene is wonderful, but it doesn't have any molecule to interact with this. So that I am doping here in the with the graphene with the fluorine molecule, and see, let us see that one whether this fluorine is acting as a doping of this fluorine is really makes a goal, reach the goal in order to detect the fluorine molecule, ammonium molecule or not. Let us see here. So you can imagine that one. It is my goal that one. This is my net of graphene here, and fluorine I am doping with this one. Then whether is it attracts the ammonia or not, let us see now here. So you know that two-dimensional nanomaterials are synthesized by either by top-down approach or bottom-up approach. Top-down approach means you are going from the bulky materials to the lower levels, and the bottom-up approach methods are from the atom by atom you are making, and you are getting a nanomaterials like a chemical vapor deposition. And for the Scotch tape method, for the Geim and Novoslav, they got a Nobel Prize for the for getting a two-dimensional nanomaterials. When these scientists told that one, yes, there is a possibility of having the two-dimensional nanomaterial, which is atomically ultra thin, atomically and ultra thin. So no one agreed that one. So someone laughed, and some theoreticians told that one, yes, may or may not be possible, but they are finally end up with yes, there is a possibility of possibility, and they made the by simple graphite exfoliation, mechanical exfoliation with a Scotch tape. They proved that one, yes, the material is exist here. So there are many methods here. So both I will touch here. Both top down and bottom up approach we used for the fluorine doped graphene here. So now first I made the theoretical studies using the Gaussian software to know the interactions between the graphene and ammonia and fluorinated graphene, whether really my molecule is interacting selectively to the specifically to this fluorinated graphene or not. So I did some optimizations result here, and in the case of this fluorinated graphene, you can see here the fluorinated graphene is having the highest stabilization energy, interaction energy here you can see, and as well as if you see the fluorinated graphene and ammonium ion. So this ammonium ion in the blood ammonia, if you would like to detect, then also it has seen the highest interaction energy in comparison to the simple graphene, that is a without doping, without dopant of my fluorine molecule. If you see, so there is a large difference between the after doping and before doping with the interactions here. So we also conducted the HOMO and LUMO gaps here, and the electrostatically how they are interacting here. And here you can see this is a the top right side is having the fluorinated graphene here. So fluorinated graphene here. Here I have the graphene, just graphene here. So you can see the there is a clear separation between the ammonia molecule and graphene without dopant here. But here my molecule is specifically attaching to the fluorinated graphene, whether it is a ammonia molecule or ammonium ion, whether it is a in the liquid or solid. So it has some interactions of specific interactions between the ammonia molecule and this here, the hydrogens and fluorine molecules. There is some electrostatic interactions, and band gap also, if you see, and the band gap has decreased in this case. So this is a 0.119 here, this is 0.121. So whereas here if you see the graphene, and this is a 0.126, here it is a graphene ammonium here. So this is a 0.136 here. So you can see there is a close interactions of between the HOMO and LUMO, and so that because of the specific interactions we found here. So once you did this one theoretical calculation, so we synthesized the graphene oxide by the improved methods of graphene oxide synthesis, and then once we synthesize this graphene oxide, so we reduce this one using the without having any reducing agent, as well as in the presence of the reducing agent, both we did here. So which one is having just heating the graphene oxide at 100 degrees centigrade for 3 hours. For the electrochemical reduction, we used the cyclic voltammetry. So where you can do the reduction of this graphene oxide by electrochemically. So both we did here because here we need to take the IR spectra. So in the case of electrochemistry, so we are using the water molecules here. So that's why for the IR recording IR spectra, we have chosen this path, which is a completely dry method instead of the wet conditions here. And if you see the characterizations of this molecule, from the thermally reduced graphene, and we exposed to the ammonia, direct ammonia gas we exposed here. This is without exposing. This black color is without exposing, and this 5 seconds and 30 seconds is exposure levels are gradually we increased here. In the case of here we gradually increase here, and you can see here in this case when the exposing of this ammonia is increasing, here you can see the shifting of this CF bond. CF bond is shifting to the lower wave number. It is shifting here in this case here. So first it is here, and then it is coming here, and then it is again coming to the here. So in this way, there is a redshift has been found in the case of the CF bond due to the interaction of the ammonia here. And theoretical FGO also theoretically also we did the FTR spectra that is shown here in the vertically shown here, and this is also having the characteristics peak of the CF bond, which is exactly matching with the experimental value here in this case. So this FTR spectra is giving a strong confidence to me that yes, my molecule of ammonia is interacting with the fluorinated molecule. And we took the idea Raman spectra also. Here in this Raman spectra, we didn't see any kind of the ID by IG ratio difference. We didn't find after and before the exposure of the ammonia, so that we can say that it is just electrostatically interacting, but not any bond formation is not taking place, because if the ammonia is attaching to the graphene, so definitely the ID ratio will get affected. But here ID by IG ratio is clearly saying that when there is no difference between the before and exposure and after exposure here. And then we went to the electrochemical sensing using the impedance spectroscopy. When we are adding slowly the ammonium ions, ammonium solution into my electrolyte, the impedance of my electrolyte is gradually changing. And interestingly, we found around the picomolars range also we found here to the micromolars range. The sensor is working in wonderfully working. And in order to know the whether this fluorinated graphene is only working, whether graphene is oxide is also working, if you see, we made the sensors with the graphene oxide and graphene and fluorinated graphene oxide and fluorinated graphene also we made here. And you can see here the other materials are not showing the much sensitivity as much as my fluorine graphene is showing here. And reproducibility also, I can't say it is 100% reproducibility, but the impedance is coming back again when we are washing with the water. So you can see that one again it is coming back to some extent around 40 to 50%. Again the detaching from the surface of this sensor, it is detaching from this one. And as you know that if we are doping with the 5% fluorinated graphene, so you can see this much of sensitivity in the picomolar region. So that's why we thought that if we are increasing the doping level, so it may increase the more and more sensitivity. So that what we did here, so we increased the levels of this one to the 20% of the fluorine here, but in this case the sensitivity has reduced a lot. So it went to the linearity portion. You can see this one, only this linearity portion to the nanomolars, it is drop it down here where you can see the 10 power minus 12. So in this case, it is just not the doping level. So optimized doping levels also important, because here the electronic properties of graphene is plays a crucial role here. And when you are increasing the doping of fluorine, the electronic conductivity of this fluorinated graphene is getting decreased, so that the sensitivity is also reduced here. And this is about the when we are exposing the ammonia to the different levels, so how the charge transfer resistance is increasing here. So it is gradually increasing and getting saturated at some point here. And once we are got a successful result with this multi-layered graphene here, so then we synthesize the CVD based graphene, which is a single layer, and then we made a chips fabricated a interdigited electrodes under the clean room conditions. And these specifications, if you see, so these are around at least just 1.5 centimeters by 1.5 centimeters chips interdigited electrodes we fabricated. On that we did the single layer of fluorinated graphene we did here, deposited using the CVD methods and chemical vapor deposition. So we made, even we exported this one chips to the UK, and for each chip is costing around the 2,000 to 3,000 rupees each chip. Each chip, it is a micro interdigited electrodes and fabricated chip, which specifically interacts with the ammonia molecules here. To some professor in the UK we did. And this is a gas sensing system where we made using the mass flow controllers, and direct gas sensings also we made using these materials. And you can see that there is a nice reproducibility is observed when the 50 ppm of the gas is inserted here. The electrode charge transfer resistance is increasing here, which is a chem resistor based sensor. It is not a impedance based sensor here, but a electronics chem resistor electronic sensor here. The resistance is getting down when we are again coming back to the ammonia gas alone here. So in this way, the conclusion of this first of my work is, so if you are carefully synthesizing the graphene, it really wonderfully acts as a for the real-time applications of the ammonia sensing. And coming to my second talk, where I focused on the molybdenum sulfide, which is also a one more layered material. So where the molybdenum molecules are sandwiched between the sulfur molecules, and these are all in the previous cases there are many molecules are reported for the MOS based sensors, like gaseous molecules, inorganic ions, pharmaceuticals, and food, even biomolecules and explosives also reported here. But here if you see that molybdenum sulfide, we found a paper from the PM Azian et al. So which is published in the nanoscale horizons. This molecule is not that much stable when it is interacting with an ascorbic acid and in the water molecules, if you see. So it is not that much stable here. So it is slowly itching the surface of this one. So it is slowly itching the surface of the molybdenum sulfide in the presence of the ascorbic acid, which is a mild reducing agent, and converting the molybdenum to the some other oxidation level. It is converting. So now we thought that one, why we can't use this one molybdenum sulfide with a graphene and make a van der Waals heterostructure, so that we can prepare a stable electrochemical sensor, which is highly sensitive as well as stable also. So that's why we prepared a van der Waals heterostructure, which is having the molybdenum sulfide and graphene are one upon each other, and these two are interacting through a van der Waals interaction, so that we call. So that's why we call it as this one van der Waals heterostructure here. We call it this one as a van der Waals heterostructure. and we prepared this one by one, layer by layer. We synthesized using the chemical vapor deposition. There is a bottom up approach, and this is a CVD synthesis where we have taken the temperature, time, and graph here. And once we did this graphene and MOS to synthesis, so we transferred onto the glassy carbon electrode using the wet chemical etching method. So it is very sensitive method. We have to do it very carefully because it's really handle the monolayer graphene onto the during the cleaning and etching the surface of the copper and silicon here. So it is somewhat difficult. Carefully we need to do, because this is a single atomic thickness layers you are dealing with this one. And once you see, once we prepared this one, you can see that when graphene and MOS2 peaks are characterized using the Raman spectroscopy here, so which simultaneously gives you that one graphene on the MOS2 layer here. So this star is containing a MOS2 structure here, and this graphene is deposited on the here in this case here. And if you see the we compared with the previous literature, we are also would like to see that one whether my ascorbic acid is really disturbing the molecule, so that we confirmed that one in this case where the graphene is not there, the graphene where the MOS2 is not protected by graphene here, so it is etching the surface. But here in this case, which is protected with the graphene, the MOS2 is stable enough, and the Raman spectra is also showing the no shifting in the these bands. You can't see here A1G and E22G. There is no shifting here in this case for the graphene protected MOS2 here. And what happened? What's wrong with this MOS2 to know this one? And we also performed this molybdenum here, and here in this case molybdenum without protected molybdenum sulfide without protection of this graphene. So it is converting to the MO6 plus and MO4 plus. It is oxidizing in this with this one here. So for the GMS, you can't find the that much high areas of this MO6 plus. You can't find, and maybe during the transfers there is a small peaks you might have got, but you don't find the MO6 plus how much it is etched here, so oxidized here. That much you didn't find in this graphene protected molybdenum sulfide. And also you can see the Raman spectra, graphene MOS2. So this is a simple graphene MOS2, and this is the after interacting with the ascorbic acid and after etching the surface with the plasma here in this case. So these are all, there is no shift in the E2G and the A1G, which are characteristic peaks of the Raman spectra. So whereas in the case of the molybdenum sulfide, simple molybdenum sulfide, if you see, so there is a shift in the peaks under the same conditions we did. So this is a ascorbic acid interacted, this is a plasma interacted here. So you can see here there is a shift in the MOS2 peaks, showing that one there is some structure has disturbed here, whereas in the graphene protected layer, so it is not disturbed the structure here in this case. And you can see the flow of PL from the MOS2 also, and compare the graphene protected MOS2 and MOS2 alone. And here which one is MOS2 that is protected with the graphene, even there is no disturbance in the PL, decrease in the intensity of the PL here, but you can see here there is a decrease and the splitting of this PL is observed in the case of the MOS2 alone here. And this is using this one we made a stable sensors here. So in the case of the graphene and MOS2, so you can see the stable sensing of the ascorbic acid, even first trial and third trial also the same here. But in this case, the molybdenum sulfide, the sensitivity signal has reduced here in this case. And dopamine, which is a neurotransmitter, so that is also graphene MOS2 showing the highest sensitivity in comparison to the MOS2 and the graphene here in this case. And the first trial and second trial and third trial is also so yeah, the sensitivity signal is getting reduced in the case of the MOS2 alone here, but in the case of the graphene MOS2, we found this very stable sensitivity found here in this case here. And using the DPV differential pulse voltammetry here, so we detected the dopamine in the presence of the ascorbic acid. So ascorbic acid, we took the here even 10 times higher than that one, but we didn't find any kind of the signals corresponding to this one. We didn't find ascorbic acid signals here. So in this way, we prepared the graphene protected MOS2 sensor, which is a highly stable as well as sensitive and selective to we made using the van der Waals heterostructure method we did here. And as I said that one, I will give you a glimpse of the energy. There is a CNT based hydrogen evolution here. So you know that people are trying to reach the hydrogen evolution on par with the platinum carbon. So platinum is an expensive material. If you would like to produce this H plus 2H plus to the hydrogen, which is a 2 electron transfer here, in the case of the platinum, it is a highly expensive. Even though the energy input is very less here, you are not applying any energy here in this case of the platinum carbon, which is around 50 millivolts of the current if you are giving. But other materials, if you see molybdenum sulfide or any other materials, if you see, you have to give the higher current here. That means if you are giving the more energy than the output energy, there is no benefit out of that one, that energy that you are getting here in the hydrogen case. So that's why people are trying with the different materials to reach to towards the lower energy levels, that is on par with the platinum carbon. So many materials, nanomaterials, nanoparticles, molybdenum, metal organic frameworks and nanorods, many are reported for the hydrogen generation, but it is still at the research and development stage only. So here I would like to show that one CNTs, we engineered the CNTs using the Suzuki coupling. So without changing the electronic properties of this CNTs here, so we made a benzene CC bonded bound this carbon nanotubes we prepared using the Suzuki coupling. So one of the interesting things are these CNTs are highly stable inks. Also, you can find you can get by using this covalently connected carbon nanotubes. We did this one Suzuki coupling for the single walled CNTs as well as the multi-walled CNTs. Both we did here, and both are showing the excellent properties of hydrogen evolution reactions has been shown here. And here is the TEM images of this one covalently connected carbon nanotubes here. And here are the results of that one. This is a palladium carbon here in this case, and whereas this SW CNTs are here around covalently connected here, this one around 200 here. But in the case of the 3D MW CNTs, so it is getting reduced here. The onset potential is near to the maybe in comparison to the platinum carbon, maybe it is around the 100 millivolts difference only we have here in this case. But in the case of the MW CNTs and other single walled CNTs, you don't find that much of the lower onset potentials you can't find here. They are having the 450 millivolts of the onset potentials you can see here. And also we didn't disturb the electronic properties of this CNTs, whether it is a single walled covalently connected single walled nanotubes or covalently connected the multi-walled nanotubes. You can see the very less charge transfer resistance and high conductivity are being shown here. So in this way, I would like to give you one flavor of hydrogen evolution reaction using a band gap engineered carbon nanotubes. So mostly, if you see the summary of my talk here, so we made by careful doping of the graphene, we made a real-time sensor for the ammonia. And in the second part of my talk, so by protecting the MOS2 with the graphene, we fabricated a very stable and highly sensitive and selective sensors for the dopamine we made. And using the CNTs, so without changing the electronic properties of the CNTs, which are covalently connected, so are showing the highest better onset potentials for the hydrogen evolution reaction they are showing here in this case. So I would like to thank ICNHTCS conference organizers, each and everyone, and Doyle Bhattacharya for organizing this and inviting me for this talk. And I will also thank Atul Wankade sir for his introduction. And you know, as I told you that one, I also would like to be young and dynamic like him. He is highly active in both academic and research. And I would like to thank my professors here who are all with the different groups I have been working. So because of them only I am able to publish and many papers here. Thank you one and all. So now, if you have any doubts, you can ask.
Yeah, the session is open for discussion.
The participants can openly ask questions, or in case of network issues, they can simply post their messages on the chat box. I will read out the messages to our speaker.
Okay, Dr. Kiran, nobody's asking.
I think nobody.
Yeah, I have few questions, right?
Yes, sir. Yes.
Not actually a questions, but just to open the doors of the new ideas. What type of interaction is there between the fluorine atom and then ammonium ion? It's a
electrostatic interaction or hydrogen bonding we are expecting. Hydrogen bonding is the most probable because in the IR spectra that we that I see, so you can see a change in the CF bond wave number.
Okay, and one more about the stability of MOS2 on graphene. On graphene oxide, there are reports that on graphene oxide MOS2 is quite stable. But what about graphene? Means up to what number of cycles you can use it for this?
CVD graphene you can use, sir. CVD graphene highly stable.
But for how many cycles?
We did 3 cycles. We did here, whatever I have shown here. But other strategies wherever I applied, so there I did a number of times. So here just for the comparison with the MOS2 and my graphene MOS2, I did 3 cycles only. But for other strategies, it is quite stable.
Okay. Yeah. So thanks, Dr. Kiran Tadi, for a nice lecture. Right. Actually, Dr. Kiran Tadi has given us a flavor of biosensors. Why this what is the importance of biosensors? As he has said that these biosensors are the rapid, reliable, and robust technology for the sensing purpose at such a lower level. He has also given us a brief idea about the importance of the two-dimensional material for for a development of a better biosensors. He has also enlightened us with an topic, say why the MOS2 cannot be used alone. What is the limitation of using MOS2 alone and how to increase the stability of MOS2 and thereby using it for a different purpose, like the one of the hot topic is the hydrogen production. So he has also touched that, and he has also given us a flavor of how this carbon nanotubes can be coupled together by Suzuki coupling reactions and thereby using it for electrochemical applications. So Dr. Kiran Tadi, really thanks for this talk, right?
Thank you, sir.
On the behalf
Thanks
of
a
the
lot.
organizers and on the behalf of all the audience, I really appreciate and I really thank your efforts that you have put in for this conference.
Thank you, sir. Thanks a lot. It's really immense pleasure to meet you. And thanks to Doyle for making this platform.
Sir, it's our pleasure to have you here.
So, yeah.
Anyways, I warmly extend my gratitude to our speaker for today, Dr. Kiran Tadi, and our chairperson, Dr. Atul Wankhere, sir. Sir, now I formally hand over the citation session to Dr. Babita, ma'am.
So, respected speaker, Dr. Kiran Tadi, sir, and respected chairperson with us, Dr. Atul Wankhere, sir. So, I, on behalf of International Conference on New Horizon and Tencent Chemical Sciences, again put forward my words of appreciation that you accepted our invitation and are with us in this international conference, gracing the occasion. So, hereby I take the opportunity to formally appreciate both of you for being here with us. So the team International Conference on New Horizon and Tencent Chemical Sciences presently proudly present the certificate to our speaker, Dr. Kiran Tadi, sir, for delivering an invited talk during the technical session of our conference. Sir, I, on behalf of the team, again, thank you once again. Kindly accept our certificate for you as a token of appreciation from all of us.
Thank you, ma'am. Thanks a lot.
Thank you for being here with us, sir.
Yeah, I am also really privileged to give this lecture. Thanks for your college to Mahavidyalaya.
So your session was excellent, and I suppose all the participants have definitely taken some key points from your session. It was simply wonderful, sir.
Thank you, ma'am.
Thank you for being here with us.
Thank you.
Thank you. So we are here very happy. Thank you, sir. Thank you.
Thank you. Atul, sir.
Yeah.
Meet you, sir. Meet you later. Catch you later.
Yes.
So we will be in touch.
We are also very eager to meet you.
Sure, sir. Sure. Okay, sir. Yeah.
Okay. See you. Bye.
Thank you, sir. So dear participants, we are happy to announce here that Dr. Atul Wankhere, sir, will be continue with us as the chairperson of the technical session 2. Sir. Atul Wankhere, sir.
Yes, madam. Thank you. Thank you.
Yes, sir.
Yeah. So good morning again and welcome all again. I
Yes,
welcome on the behalf of ICNHTCS-2022 and ISAS Nagpur chapter. I welcome today's honorable speaker, Professor Satish Patil, sir. Satish Patil, sir. Yeah. Nice to see you, sir. Nice to see you. I'm fortunate that I'm hosting you again in Nagpur, but this time in a virtual mode.
I know. Yes. Okay.
So, speaking about Patil, sir, he don't need any introduction, and a person like me will be introducing Patil, sir. It's not a good thing, but still, the organizer has given me this responsibility. So, talking about he has done his PhD from Walpurt University, Germany, followed by the postdoctorate from University of California, Los Angeles, USA. And directly he joined in IC Bangalore in 2006 as an assistant professor, thereby promoted to associate professor in 2012, and to the post of professor in 2017, which he is holding still now. He is working as a professor in a Department of Solid State and Structural Chemistry Unit, C.V. Raman Avenue at Indian Institute of Sciences, Bangalore. He has several awards to his credit. He is a proud recipient of Microsoft Research India Outstanding Young Faculty Award, then A.V. Ramarao Research Foundation Young Scientist Award. Of course, when he was young, sir has not mentioned the year, otherwise I would have also uttered that. Then he is a proud recipient of Professor Kaushal Kishore Memorial Award from the Society of Polymeric Sciences India. He is a bronze medal awardee that I too know. He is a bronze medal awardee of Research Society and Material Research Society of India, Young Associate of an Indian Academy of Sciences, Bangalore. Then he is an INSA Young Scientist awardee in 2009, Young Affiliation of the World Academy of Sciences, Suvarna Jayanti Fellowship in 2013-14, and he's a fellow member of an Indian Academy of Sciences, Bangalore. To his credit, he has n number of research paper published, of course, in a very reputed journals. Along with that, he also holds a position as the reviewer and the editor and co-editor of various journals. To his credit, he has around 10 plus number of patents. Few of them are Indian and many of them are US patent too. Sir, on the behalf of our organizing committee, I welcome you, and it will be our pride that to hear your lecture once again.
Thank you very much. Thank you, Atul. Thank you very much.
Handing the platform to you, sir.
Yes, I will try to share my screen. Yeah, just a minute. So you guys are seeing when you see the slides, please let me know. Yeah.
Yes, it's perfect, sir.
Yes, sir, it is visible.
Perfect. Okay. Good. Okay. So once again, I really appreciate. Thank you very much, Atul. It was wonderful to see you again on virtual platform. We met you in Nagpur, I remember, a couple of years ago, before pandemic, right?
Yes.
Yeah. Okay. So let me also take this opportunity to thank Organizer for giving me this opportunity, especially my batchmate, Dr. Sunil Dahri we did a master's together in Aurangabad. So thank you very much for everyone. So let me start today with, to give sort of I have prepared a lecture. It's very general, actually. I don't want to make it very, technically very complex, so that I just simply motivate a large number of students, community listening to me today. So the idea is to give a bit of a flavor of our research, but essentially, how are we going to motivate people to, to participate in the research what we have been doing at IISc Bangalore. So this is the title. This is just a exciting world of molecular electronics. But let me just start by asking just a simple philosophical questions. So why do we practice science? What is the main motivation of practicing the science? So the major goal of practicing science is we try to understand the complexity of nature, and we try to also make some artificial things. We try to come over some of the difficulties, provide technology. One best example of how science serves the humanity is the development of vaccine. You see, during pandemic we had a terrible crisis. So we all have gone through, each one of us. You talk anybody in the world, some of other way means we got affected. And today we are trying to come back to the normal. So science has rescued us. So that's a big thing science can do. Unfortunately, in our country, we don't get that much appreciation for a scientist. But eventually, we have to really keep our quest relentlessly to asking these questions. Why do we practice science? And that's very, very important for all of us. To become a scientist, we have to very, very focused. We have to have our goals to be defined, objectives to be very well defined, and then we have to pursue towards that journey. So with this, let me give some few examples what science has done so far, again, just to excite you to take it forward. So this is the world's first computer. I think perhaps people in VNIT has seen a couple of slides in the past when I visited in the Nagpur. You see, this is the world's first computer. You see that it requires a humongous space to even to store it. You need a massive amount of a room and infrastructure. It requires, and this is a very, very slow computer. To operate a computer, you need several human beings to just to turn on the computer and to process the data. And multiple processors, a big room apart from the space, it needs a lot of electricity to run this computer. You see these all two, a gentleman and a lady who is standing here trying to understand these processors here. Let's see what happened to today's computer. Today's computers are becoming tiny, smaller and smaller and smaller devices. We can hold it in pocket, and they are fastest computers if you compare 1980s supercomputer. So-called a 1980s supercomputer now you have in your pocket, and which is really connected to the rest of the world. And there is similar with the cell phone. Cell phone. This is world's first cell phone. You see that in a Dr. Cooper, Motorola, it made this first cell phone. And he was delighted to talk with his colleague next room. And this is this cell phone weighs 3 kilograms. It's a big cell phone, and you just talk with people. And this happens during my lifetime. Just imagine how the transition in a cell phone. The way we connect now. If I see just when I go out of my apartment, we see I'm delighted to see a security person can speak to his family wherever they are on a smartphone. They can make a video chat and they can talk with each other. But just my own personal story, when I went to Germany in 2000, I was struggling to connect to my parents to even 2000, just 20 years ago. So that's what science has done. Now you see what science has done. So you see the cell phone now. You can connect to the whole world. You can connect to the globe. You can access the information. You can ask questions to the Google. Any complex things we have in life, you can understand this one. So this is something I consider a big gift to humanity from going from here to here. And then especially for education in our country, especially during pandemic, where we could teach people wherever they are. And now today I'm sitting in my house, I'm connecting a large number of people with very simple ease, actually, with my computer, and I'm connecting to your computer. So we are exchanging the information. So, but there is a lot of work went behind doing this. This is not a simple journey. There are several Nobel Prizes people have won, making computer from here to here, similar with the cell phone from here to here. Let's try to understand what went in yours. What is the science behind your cell phone? There are different parts of cell phone. You just hold it down, ask this question: how scientists has developed these cell phones, what we are using today, so-called iPhone or smartphone. There are several interdisciplinary branches of science have come together to make a cell phone, what we see today. And there are several Nobel Prizes have been won by making a cell phone itself, simply. So you see that the display screen today, we see a immensely, beautiful display. What we see when you take a picture, you see delighted to see that what the picture is very, very beautiful. And you kind of videos, you see the high display today, and kind of information you get it is because of this something called organic light emitting diodes. So they have been integrated today with the cell phone. In the past, it was the LCD screen, and now we have a pixels by pixels. There is a tremendous improvement in the way we perceive the information. But it is not again an easy journey. A transition from a conventional silicon semiconductor to use something called organic semiconductor, and use those light emitting diodes and integrating with the cell phone and improving the efficiency. So this is something which we should appreciate what science has done, and how we today we perceive the information. But there is a flip side always. What again, how science has harmed the environment actually. So this is something which I will walk through. Now let's look at the today's requirement of energy. Okay, I think many of you, simply turning on the fan in the room, simply turning on the light in the room, but what is the source of this energy? How are we going to do you really understand this one? So where it is coming from and what harm it is doing in a return to the environment? So this is extremely serious, and here is major damage science has done, and now it has standing right in the door asking questions. How are we going to solve this problem? So this is where we start using a laptop, which is currently I'm using my MacBook to connect to you. I start consuming the electricity, but I should be very simply recognize the fact that where is this energy coming from? How I'm going to really using this energy? How I'm producing energy has been produced. So this is the simple device which is consumes 1 watt power. But let's look at a other aspect of the energy. And so just to running industry, producing cell phones, okay, large number of cell phones, billions of cell phones have been produced today, are running a pharmaceutical industry of making anything which is useful in the world. You need a tremendous amount of energy, and we consume energy everywhere. Let's not worry about these units. Don't get confused. These are petajoules and ettajoules, but let's focus on one unit, something called terawatt. And now you understand how many zeros are there. Terawatt means. So simply for the lighting purpose, we consume terawatt scale energy. So that's a humongous number, and we don't know from where it is coming from. And it is and we don't know in the return how harmful these resources are. What are we burning and how are we destroying the planet? Let's try to go forward and see that how we as a scientist, how we can contribute to those aspects. So this is again today's consumption of a global energy. You see that how do we produce energy? This is the scale, simply terawatt hour, and a time scales here. Now on my x-axis here is the time scales, and this is the global energy consumption. You see that in 1800 we were consuming a traditional biomass. We didn't have a means of connecting. We didn't have grid. We didn't have many other things. How do we connect it? But now in 2019, today we require tremendous amount of energy. But how do we generate that energy? Majority of the energy generated by burning coal or oil. So people don't know. They go to the simply a petrol bank or a gas station, fill their car, and they run again forward. But what is the source? From where is the petrol coming from? It's very, very important as a scientist to ask that question and minimize the usage. At home, each one of us has to play a very important role. I'm going to show some very scary pictures in next couple of slides, so you understand that my sort of appeal to all of you, how we can minimize the use of energy. And then we'll see that how are we going to address these questions. You see that in this plot here, essentially, other renewable energy consumption is very small because we don't have a technology, we don't have a means of harvesting the renewable energy, but we have grown so big now. The planet is so advanced, we can't live without computer. Perhaps we live with today. If you ask a child, a school-going child, he's happy to be stay away from his parents for a day. But you just take away the cell phone device from a child for 1 hour, you see the irritation. Okay, so we got used to with the technology. We got used to with the kind of the lifestyle we live in today. So as a result, what happens is we need to absolutely meet those requirements. But how are we going to meet this requirement? How what in return? I said how we are destroying the environment. So let's look at some of the picture. What happens to the planet now? What is the temperature today? There is something called global warming. You must have heard it. You must have read in the newspaper. You must have seen in Facebook. This is where we are heading at. We are heading at a beautiful green planet to a very scary planet now. You see, this is a picture here, and global warming is enhancing the temperature. So, we say our body temperature increases, we say we got a fever. So here see that now we are having +1 degree Celsius. So means in Fahrenheit, it is up to 1.98 Fahrenheit. So you are already warming the planet. But as a human being, when you have a fever, you go and take a paracetamol, you know, how are we going to treat nature now? How it is going to react? If a warmer planet, how it is going to react to all of us? This is not a really good news. I showed some of the very beautiful images in the beginning saying what science has done, how science has saved humanity. In return, science has also done a lot of damage to the planet. Let's look at this. What does it mean, the warm planet? Okay, what causes, what are the drastic effect it brings along with us, and how are we going to struggle to repair those effects? Let's see that. This is a Antarctic, the ice is melting there. Constantly ice is melting. You see that this is something, a very, very drastic effect of warmer planet. This is one example. You see that this is flood. This is flood in very, very advanced country. It's not like, you know, flood in a country where they do not have a means of tackling the flood. But this is very recently in Germany, where towns have been swamped. They had no idea about how to deal with this flood actually situation. So there is a incessant rain, and we already experienced such flooding in Maharashtra, flooding recently in some part of the Maharashtra was very badly flooded. They had never seen such calamity before. So warmer planet is started showing the sign already. Perhaps the temperature, Nagpur seems to be very hot in summer, but now you see that what temperature has gone in Nagpur now. Nagpur in summer, it is increasingly difficult to just to go out in a, let's say 12 noon out of the house and, you know, go for a shopping, or go for a bicycle ride. It's very, very difficult to just to come out of the house in a, but so warmer planet has started showing a very drastic signatures, which we need to tackle it now. How are we going to tackle this one? So a few more examples. So this is like, you know, now let's look at how are the challenges and how are we going to tackle. We have solutions, but we have to extremely careful of addressing this question. First, we have to minimize the usage. Don't use wherever it is not necessary. Absolutely. Don't use the fan, which is simply running a fan. Don't use the refrigerator if it is not required. Don't use actually the lifestyle, the very Indianized lifestyle is the best lifestyle. So we don't try to challenge nature. Unnecessary having a turn on 4 computers in your house is not absolutely required, because you are in return. So that's the first mantra which each one of us have to adopt, saying that we are going to be a climate, sort of a warrior. We are going to join hand in this journey and make people to understand that turning unnecessary uses of energy is going to harm the planet. So this is very, 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 very important for all of the scientific community here listening to me today. We have to, each one of us have to play that role. So now the question is, where do we need that much energy? So this is so we call it as a 14 terawatt energy challenge. So this is a collage map of a, globe. So everywhere is not night. You see that it is, sort of a collaged image of, global map. See, it's a very brightened. We see nature does beautiful things. Early morning, we have a beautiful sunrise. We start a fresh day. We forget what happened in our life, all the negativity in the previous day. You start with the day with a very beautiful, bright sunlight. But in the night, we need something artificial sunlight. It's hard to imagine how to live without electricity. So this is a brightened world, but you see that some part of the world is not yet completely brightened. India is fairly good, thanks to the recent, there are many initiatives by the government. In India, the grid deprived community is very small. Maximum people do have a basic access to the light. But there are still a large number of population perhaps still missing out the light, because light is absolutely important for all kinds of things actually. In addition to food, you need to have a light. Without light, it's very hard to imagine the life. But some part of the planet is not yet having a complete access to the grid. So they also deserve to have a access to the grid, and we are trying to provide a cheap and cost-effective solution to this community, saying that we can provide light to them also. So this number is increasingly going to increase day by day. It's not going to be stay same. So as we move forward, we need more and more energy to just a simple light. Okay, to turn on from in the night, turn on your room light, turn on your bedroom light, whatever the light it is. But then how are we going to generate this 14 terawatt? It's a humongous number without harming the planet. So what are the questions we have it here? So let's look at the possible solutions. What is the light so far we have? Thanks to, again, Edison, so whatever the incandescent lamp, you see that, because there are efforts, there are tremendous amount of effort. People are trying to address the question, minimize the uses of this energy. Then you need to make a very efficient light. Okay, so this is where our research in Bangalore also, I will show a couple of slides, how we also try to do cost-effective light. So this is the incandescent lamp. You must have seen it, and this lamp is a most inefficient way of utilizing the energy. So you have a filament here, this metal filament. Essentially, you warm the filament, you apply the voltage, and you glow the light. Okay, so it's a thermal way of converting energy to a light energy. And we have inside the argon inert atmosphere, and we have a filament which is glowing there. But 60% of the light will be wasted as a heat here. There is no way we can convert. You see that is 40 watt bulb is not bright in the room as 1.5 watt bulb. So you need to supply a tremendous amount of energy to glow the light, and that light will be a dim light again in the room for reading purpose or whatever purpose. A small area of a light, perhaps you might be lightened, but that is again, the lifetime is very, very low. You keep generating waste. Okay, imagine that 1,000 hours don't believe this number. When I was a child, we used to turn on the light and tuck, it will go in a minute. It depends upon how stable your source of a power it is. If your power is unstable, it's a filament which is glowing by heat, supplying the heat. And if you have unstable source of electricity or source of a voltage, it will just blow up actually. So that is the reason this is not considered as a light. But again, this provided this, we use for hundreds of years, this one. Then comes the fluorescent lamp. Then again, how to make it efficient use of energy. There is a 10 watt. Now instead of 40 watt, I use 10 watt. But then the lifetime of the light is 10,000 hours now. So you use light much, much better, and this you consume less energy and you brighten the house. So you see that this 10 watt lamp actually is much better. You must be having it in everybody is using that. Incandescent lamp is banned, at least in Karnataka. I don't know about Maharashtra, but people, we can't go by and buy incandescent lamp anymore now because of this problem with the incandescent. So it's again, the next generation is LEDs. People now, you see that again, now you reduce the power from 10 watt, you go to 1.5 watt, but the lifetime of this light is 50,000 hours now. So here are many challenges for a chemist, for a physicist or engineer, how we are going to make cost-effective LED. You must have gone in the shopping. I think if we are not done, please go and purchase a light. Go and ask for a LED light. LED lights are not commonly available in many shops because of the cost and because of the they don't produce a lot many more actually. There are many problems with LEDs. Fluorescent lamp is decent, but again, fluorescent lamp works in the mechanism of a phosphorescent mechanism, where you have a very toxic metals inside these lamps, and these toxic metals are again very harmful. How are we going to really recycle this lamp? That's a question with the fluorescent light. So essentially what I mean to say is, if you want to make it a LED for 10 rupees, you have a tremendous challenges in the research. How are we going to make it cost effective LEDs? How are we, you can't simply go and convince a person who earns a day-to-day 50 rupees. You say, I'm going to give you the best light for 300 rupees. Nobody's going to purchase. How harm it is for environment. People will go back and purchase incandescent lamp. Incandescent lamp is for 10 rupees and LED lights is for, let's say, for 300 rupees. So the challenge for all our scientific community, reduce the cost of this one. What kind of technology is gone into build LEDs? Can you make it a a new semiconductor? Can you develop a semiconductor which are cost effective and make it a light emitting diodes for cheaper and cheaper and sell it for 10 rupees? So this is the bigger challenge. So you are working in the area of energy and you are addressing the question of this global energy by making a better LED. So that's something, one area of research in my group. As well, we try to make organic light emitting diodes instead of using a conventional semiconductor. So this is I will again touch upon a little bit later. But let's look at historically. See, this picture I think is very, you know that who is I'm referring here. So here is, you can see that the discovery begins with a lot of mockery, lot of struggle. It's not easy. Okay, so discovery for a scientist, for example, when he's Edison first time showed a light here to the world, saying I have a light. Then what was the light efficiency you would describe in lumens per watt? That's a unit for describing light efficiency. He had 1 lumens per watt, and it's like a candle actually. And there are many people in the conferences made fun of Edison, saying that, look, my candle is much better, brighten than your light. But today, till now, at least for 100 years, thanks to Edison, we had a light. So, don't get discouraged if you begin with anything you're seeing as a scientist, you should observe very closely. You have a tremendous potential to deliver things which you have to constantly, relentlessly, you have to keep chasing those goals, and you have to say that, okay, I'm going to make a difference, and I'm going to make a difference. So as a part of your PhD thesis, as a part of your, any research program you're developing in your group, you have to have that passion. Otherwise, you lose the bus actually. So here, essentially, Edison, if you go to, I have visited many of his museum in London. You see, these are some of the pictures they have stored here, and you see how he just went through entire periodic table. He screened out all the possible elements and start glowing them, start applying heat in a vacuum, and see that which is the best, which is the cheapest one. So his mantra was very, very clear. He wanted to deliver the light, which is very, very cost effective. And then he made a very important statement. He said that I have not failed. I just found 10,000 ways that won't work. So today's scientists are not, we don't even accept the failure. We say everything is working actually. So, and then we end up writing a paper saying that this is the result, I got it, and I'm publishing a paper. So that's where the difference with the previous era, where they said like, they were accept defeat, and then they finally came up with the bigger invention, and that make a big difference in the humanity. So this is just a motivational slide about how we can contribute in LED area. So you can, I little bit of explain and spend some time about Atul. You have to stop me. You have to, whenever I'm, I have a habit of going for hours and hours. So just you stop me wherever I'm exceeding the time. Okay. So, all right. So let's me just start about in elastic scattering in the fluorescence here. This is the major problem with the LED, the one light which you are using it. So when the light goes bad, please, I again appeal to all of you, do not throw it anywhere in garbage, because it contains some mercury. So it's very dangerous. It contaminates your groundwater, and you start having many people having terrible health issues. So you need to really learn how to really make recycle of those lights, and then don't just simply throw it away or give it to your maid saying that throw it in a dustbin. So it's very important you just take care of that light very, very carefully. And then this is the major problem where people sort of not aware about what is there in that light. When it goes bad, just the people throw away, it goes in garbage goes somewhere, and then it eventually contaminates a groundwater. And that groundwater, you use any RO filter, it goes in your body at ppm level, is sufficient enough to damage your lungs or carcinogenic. These are extremely dangerous methods. So let's look at like little bit up now how we are trying here actually. What is our role now as a research group at IISc? How are we going to address these questions? So we use a different class of material. We are sort of by training, I'm an organic chemist. So we use molecular semiconductors. So we like, make molecular semiconductors. Our motivation behind these molecular semiconductors is why we use molecular semiconductors. That's the first question we ask. are we going to make a really difference in existing technology by using molecular semiconductor? So where we say that, okay, the major, the advantage of a molecular semiconductor is they are soluble in common organic solvents. As an organic chemist, you must be knowing that molecules are soluble in a range of organic solvents, whereas if you take a silicon, it is not soluble in organic solvents. So that's the beauty of these material, where they are solution processable. Once I make solution processable semiconductor, then those semiconductor can be printed. Okay, that can be, I can entirely reduce the cost of fabrication. I gave you one example of LED. Now, if I want to make a LED out of this one, I don't need a very sophisticated fab lab to make LED. I can simply make LED by printing. This is what I have shown here. I can print a ink on any substrate. I can make a flexible, sort of, this is the cell phone charger, is one of the, recently, sort of a commercial product where people are launching, where you use solar cells to charge your cell phone. You don't have to carry, your charger, and you can simply use a free energy, which is available, comes from the sunlight. So these are the sort of a motivation where we say, this is ink. Actually, if I'm seeing my arrow, I don't know my laser pointer is whether it will work or not. Does it has a, okay, this is, you are on mute, Atul. So my arrow you are seeing, right? Right? Are you seeing the arrow here? Yeah, I think you are on mute. Okay.
Yeah, we can see it.
Okay, good. All right. So this is something. The question is here. It's a low cost of fabrication. We can make an ink in any common solvent. They are lightweight. Silicon panels, you must have seen. Suppose if I get a solar panel, silicon panel on a rooftop, it's very heavy. It's very difficult to sort of use it on the rooftop. So if the buildings are weak and we can't really integrate on a weaker buildings or on a hut or anywhere in different parts of the country. So where this is something with lightweight and flexible. And also you can tune the physical and chemical properties. You see that actually a simple example as a chemist, you can go from benzene to naphthalene to anthracene. You keep tuning the HOMO-LUMO level based on your molecular orbital theory. You see your potentials, the position of a HOMO-LUMO level will change with respect to the vacuum. So that's the way you can tune the absorption spectrum. You can tune the emission spectrum. That's what I mean to say. As a chemist, you have a wonderful opportunity here where you can tune the physical and chemical properties as you desire. Whereas in conventional elemental semiconductor, if I give an example of the silicon, it's very, very difficult to tune the band gap. It is a fixed band gap semiconductor. You cannot really tune by doing such substitution reactions, what you do for a molecular semiconductor. So this is sort of a motivation for our research, where we say, we make these LEDs, we make solar cells, we make, are very advanced up to electronic devices by using molecules rather than the elemental semiconductor. So going forward, okay, so let's ask this question a little bit now. My talk is getting technical. So you see that what is the difference between carbon and silicon? They belongs to the same group in a periodic table, but the carbon and silicon here, okay, so there is indeed a difference. Okay, they can have similar properties to silicon in terms of valency, in terms of but there is, you can make it, you can grow carbon chain long. Okay, you can make it such a pi conjugated molecule out of a carbon by doing it. Then it acts as a semiconducting electron material when these pi electrons. So this is just a pi orbital, alternate double bond, single bond, double single bond. So you have a delocalization across the backbone, and that gives a semiconducting property. So this is something very, very important first to understand, and then you can make it you can pack these materials, you can make a solar cells. So now ask the questions, I get a free slide now. How I'm going to make it? If this is true, I said we are burning fossil fuels, we are having a lot of issues with the planet. Can I use a free sunlight and convert into a electricity, and can I store it, or can I supply directly to the grid? But there are many challenges here again. So as the first said, don't use it unnecessary, don't make up unnecessary use it, because this is not the solution again. But you can choose the lesser evil here. You can perhaps go for this solution better than what you are doing it today. But first thing is better to not to use unnecessary electricity wherever is not required. But solar can provide you solution. There are issues with this technology, which we all of us are working, trying to address those. But however, now let's try to understand how solar is going to rescue. Okay, so this is the energy is very, very important, which you get a free form of a sunlight. You shine on a solar panel like this, and you can either supply to the grid, and that gets supplied to the home as a consumer market, or you can store by using a batteries. So there are possible ways of doing it, because in a night time when you don't have sunlight, you need to store the energy what has been harvested in a daytime, so for an entire day. So it's very, very important for you to have a integration of a battery to the sunlight and store the energy and supply to the grid. So let's understand what is the source of energy in sunlight, what are the properties of the sunlight. So there is sun is a very hot sphere. It generates 1 million degrees of extremely hot. So we have this stories in Ramayana how Hanuman went to catch sun, and so those are I find it very we find it exciting when we were a child listening to those stories. But it is an extremely hot sphere. So there is, if you understand what reaction takes place on sun, there is a fusion reaction that gives a, I don't know how many zeros are here. So it's a very hot sphere. But these free hydrogen ions absorbs the majority of the sunlight, and it emits, it acts as a black body now. So the sphere, the surface of this photosphere is 6,000 Kelvin. Now it's still very, very hot, and it start, passing the light towards the earth. So a planet being far away from sun, so you get essentially the light passes through a different zones of atmosphere, and it starts scattering, absorbing. Eventually it passes through ozone layer. That's what people are saying. Ozone layer is very important because it absorbs the high energy photon from the sun, and it one can avoid the skin burn and other effects of high energy photon. And then maybe others can mute Sandeep Haldar.
Haldar sir, Sandeepan Haldar sir.
I have muted him. Okay, don't worry.
Yes, sir. Are you saying something?
Okay, now I think I'm audible, Atul?
Yes. Haldar sir, you have to mute yourself.
Okay. So essentially what happens is basically the light which reaches to the earth is passes through the different zone, and we need to understand what we get. So this is something which we get on the planet where we can harvest, we can convert into a useful form of energy. And this is the free light. This is where the challenges are. Renewable energy, how are we going to make it cost effective? Solar cells. So again, you see that this is the emission spectra now. The light comes in a different form. It's a distributed wavelength. It comes in a UV, which is a sort of a very high energy photon, visible, which is very important, what all of us see. And we also get a tremendous in a lot of light in infrared part of the spectrum. So if you want to really harvest simply a visible part of the spectrum, you have to do a play with the band gap. You have to play with the right kind of a semiconductor, right kind of a material, and how are you going to make it? Solar cells now. So there are different people thought about it. I think scientists have been constantly working from ages now, where they always felt it. There are issues with the solar cells. I mean, there are these global warming issues are going to, they anticipated a 50 or 100 years ago, saying that we have to generate, we have to trap this sunlight. We have to, essentially convert this free sunlight into a useful form of energy to avoid the issues with the planet. So, Atul, how much time I have?
Another half an hour.
I can go another half an hour?
No, it's 15 minutes, 15 minutes. Yeah.
No.
All right. Okay. So I think that Dr. Bhattacharya is saying like, I can't go for another half an hour. All right. So, okay, another 15 minutes, right? Okay, so let's look at what has been done. Let's look at the historically how solar cells have been developed. So the first generation of solar cells are silicon, and they are dominant in the market today. They are the one which we can, you see everywhere. They are very robust, based on silicon. single crystalline silicon, and they are not at all cost effective. There are many limitations with silicon solar cells. Where first of all, the efficiencies are pretty good now. I think numbers have achieved much better. It has almost thermodynamic limit, but it is not at all cost effective. It is first of all converting a raw sand into a silicon panel is extremely energy intensive process. So you need to really heat a sand at very high temperature and convert into a model actually. That itself is a very, very energy intensive program, and one has to be very careful about, so that's the reason you don't see silicon, right? Much of, otherwise we could have solved all the energy problem, saying that everybody has a silicon panel in their house and we make a transition from fossil fuel to the silicon. So that's not very straightforward because of the cost, because of the, again, the availability of the silicon, because of the kind of model you produce. But like recently, the cost has been dropped dramatically, but still it is very, very challenging. So this is something which was done in a 1943, where Chapin and Fuller in Bell Laboratories started working on the silicon, and then they made a cell. To come over some of the limitations or difficulties of the silicon, there are second generation solar cells have been made. Those are all thin film solar cells based on amorphous silicon. They are based on CIGS, cadmium telluride, different types of materials here. Amorphous silicon is again still an elemental semiconductor, and then you use materials which are based on cadmium telluride, CIGS, and all those elemental semiconductor, and make amorphous silicon solar cells. So to come over the cost, these are some of the proposed alternative materials. But again, they face a lot of limitations. For example, cad telluride is very, very sort of a toxic material. Amorphous silicon has a lot of defect, but you see that from single crystalline silicon to amorphous, there is a change in the material requirement. You use a 100 to 250 micrometer thick film when you use single crystalline. When you use amorphous silicon, you use a thinner cell, because there is here the single crystalline silicon solar cells is the indirect band gap material. It's a lousy material for a light absorption. Its absorption coefficient is very, very small as compared to the amorphous silicon other materials. So you use less material to harvest more light when you switch from first generation to the second generation. So this is the major advantage, but in return, the lifetime is very, very poor for all these other materials. Whereas, this silicon solar cells are very robust. You have 25 years of lifetime, but when you switch to the thin film solar cells, you have to have a very, you gain over the sum of the limitations, but however, we face other limitations. So that has been still a challenge and ongoing work in the community who are working on solar cells. So here now, third generation, there are a range of materials people are currently working on across the globe. A large number of research communities engaged to come over some of the difficulties which has a single crystalline or amorphous. There it's a dye-sensitized polymer based solar cells, which my group is involved at IISc Bangalore. Multi-junction solar cells, there's recently a buzzword called perovskite solar cells, where a large number of people are working on those materials. They seems to be a wonder material. They at least give it the first impression that people can solve energy problems, but there are again a lot of, it comes with own limitations and issues here. So this is the current status where the solar energy can be converted, but by using a range of different class of materials. So it has its own positive, pros and cons. Every material has its own pros and cons. So then with Stabler-Wronski effect, I will not explain this one because of the lack of time, but there is indeed the limitation comes from this major issue with the Stabler, and everything works on PN junction if you want to understand the physics behind these solar cells. So I think people are asking this question for the third generation, will they ever come to market? So this is the questions which I will be very nervous to answer that, but perhaps this is an ongoing debate whether will they ever come to the market. So but just rationale behind silicon, always always the question is availability. You look at how much silicon is available. Silicon is earth abundant material. We can go terawatt scales. If you look at here, abundance of atoms of element, it is as good as oxygen. So silicon is available in all forms of rock, and it is distributed across the globe. It's not only dominated by one part of the globe. So if it's available everywhere, and then it is that's one of the rationale behind why to use silicon. And this is where this is a very exciting comment made by Donald Sadoway. Here is a professor in MIT, works on energy. So if you want to make a solar cell dirt chip, you have to make them out of dirt. So that's very, very important statement which he made in the context of batteries, but it is true for even for solar cells. So these are some of the ideas which we pursue in our group based on perovskite, based on organic solar cells. Quantum dot we don't work, but this is something, again, a material of people are trying to engineer materials and make cost-effective and cheaper solar cells. So this is where we currently stand. I will not really go to all the details, physics about it. So this is some of the animations which I can share, but there are many challenges, which is why we, one of the major challenges, how are we going to go beyond Shockley-Queisser limit? So that's a thermodynamic limit. This is the basic fundamental questions where we try to understand in our group, how are we going to address these loss mechanisms in solar cells. So this is some of our work which has been published in some of the journals where we can look into it, where we try to address losses in semiconducting polymer and come over some of these difficulties. So, and we also have some very unconventional way of making solar cells, where we call it a singlet fission based solar cells. So this is the ongoing work in our group. So this is because of the lack of time, I will not be able to cover all these things. So basically, we work with a large number of people across the globe because we are addressing energy problems. It's very, very important to talk with people, collaborate with people. So we have been fortunate enough to work with wonderful collaborators across the globe in Cambridge, in Imperial College, in here in Jawaharlal Nehru Center, and in TIFR Mumbai. And some of the all the work which goes in my group is done by extraordinary talented grad students actually. So they are the best to drive these problems actually. So this is Tushita Mukhopadhyay. She just graduated from the group, working as a postdoc in Johns Hopkins now. So, and then he has one postdoc which has been working with me on these kind of material. But these are the two people who were driving this research on organic solar cells. But we have a big, large research group at IISc, where it's a combination of a chemist and physicist, where we asking this question, can we solve this energy problem? So with this, I will stop here, and I will be happy to answer any questions which you have.
Thank you, sir.
Yep.
Yes, sir. Participants are requested to place their questions in the chat box. If there are any, we will read it on their behalf. Yes, any questions?
There are a few charts actually I could see. Okay, but it's just a comments. I think it's not a question.
Yes, sir, there are compliments, sir, actually, for your session. It was indeed a wonderful session, sir.
Thank you very much. Thank you.
Sir, I have one thing. What about that third generation or dye-sensitized solar cell development? What are the real challenges?
Yes, so dye-sensitized solar cells, there are challenges because I think the majority of the issues are with electrolyte, because the best solar cells which works in DSSC is when Michael Gretzel made it, they were on liquid electrolyte. Then there are solid electrolyte variants were made, but then efficiency is become a issue. So then the perovskite came in picture. Then what happened? There is a major, it's a similar device architecture. So people did the transition because this material seems to be giving a very high efficiency compared to DSSC. So the DSSC solar cells were projected certainly in the past, saying that, okay, they can be alternatives for some of the applications, but they took all of a sudden this backseat because of the perovskite. So perovskite solar cells is much simpler, you see, to make also. Yeah. So that's the reason it is much.
Can you take care of that?
Yes, yes. Somebody's others can mute. Maybe who is this person is? Yes, Atul, tell me. Yeah, please.
Yes.
Fine.
Okay, sir.
Ah.
So thank you, Professor Patil, for an exciting talk on an exciting world of molecular electronics. The session started, or the lecture started, with an eye-opening question that why do we really practice science? This is really the question which has opened the eyes. Then he talked about, then he first underlined about the importance of electricity conservation and conversion for saving our Mother Earth. Then the next, what he introduced was the work they used to do on organic LEDs, development of organic LEDs for development of solar cell for efficiently converting sunlight to electricity. Sir, this topic really has a tremendous inertia. One cannot start working on it directly, but yeah, you have provided us the potential to overcome this inertia for efficient conversion of the sunlight to electricity. Overall, the talk was very good, nice, informative. With a limited time constraint, you have touched enough portion. Really, thank you for that.
Thank you very much. Thank you.
Sir, thank you so much from the organizers for your wonderful talk on exciting world of molecular electronics. You have appealed to all participants to minimize the energy conservation, and we as the organizers from this platform also want to appeal the same to all, that minimize the energy consumption and reduce the resources however we are possible, and use the alternatives for the same. Thank you so much, sir. Thank you so much to you and to Atul Wankhede, sir, also from the organizers. We team the international conference on New Horizon and Trends in Chemical Sciences.
Sure.
Thank you, sir. Sir,
Thank you.
kindly allow us some minutes for the formal citation and placing our gratitude in terms of certificates.
No problem.
And to do the honor, I am calling upon Dr. Doyle Bhattacharya. Ma'am, please.
Good afternoon, one and all. Again, a very warm welcome. And I'm very thankful to our speaker today, Dr. Satish Patil, sir, for your wonderful and informative talk. And I also equivalently extend my gratitude to our chairperson for today, Dr. Atul Wankhede, sir. I take the opportunity of proudly presenting the certificate of appreciation as a token of respect to our eminent speaker, Dr. Satish Patil, for delivering an invited talk during the technical session of an international conference on New Horizons and Trends in Chemical Sciences, ICNHTCS-2022, organized by the Department of Chemistry, Dada, Ramchand, Bakhru, Sindhu, Mahavidyalaya, Nagpur, in association with the Indian Society of Analytical Scientists, Nagpur chapter, during the 25th and 26th March 2022. Sir, I virtually hand over the certificate to you in your honor. Please accept it.
Thank you very much. I really appreciate it. Thank you.
And I equivalently extend my gratitude by proudly presenting the certificate to our dear Dr. Atul Wankhede, sir, from BNIT. Sir, kindly accept this certificate for chairing the technical session of an international conference on New Horizons and Trends in Chemical Sciences organized by the Department of Chemistry, Dada, Ramchand, Bakhru, Sindhu, Mahavidyalaya, Nagpur, in association with the Indian Society of Analytical Scientists, Nagpur chapter, during the 25th, 26th March 2022. Sir, we are very thankful to you for your cooperation, for making this session a successful one. Thank you so much, sir. Kindly accept the certificate, sir.
Okay. Thank you.
Thank you, sir. It was very good to have you both over here and for the same technical session. Thank you, sir.
Thank you very much. Thank you. All the best.
Thank you, sir. Dear participants and the dignitaries, now we proceed over the third session of today, and we have our eminent speaker, Dr. Shyam Perugu sir with us, and our chairperson for today is Dr. Sunil Ganatra sir. Shyam Perugu sir, are you there?
Yes, madam, I am there.
Yeah, yes, sir. Yes, sir. Okay. Thank you, sir. Meena Joshi. Now I hand over the formal proceedings to Dr. Meenal Joshi for the third technical session. Over to you, Meenal ma'am. Please go ahead.
Ma'am, thank you, ma'am. Thank you very much. Now I take this opportunity to welcome all. A very good afternoon to all. And I am Meenal Joshi, Chemistry Department, Shri Ramdev Baba College of Engineering and Management. I welcome you all in the third technical session of day 2 of ICNHTCS-2022. I welcome today's speaker, Dr. Shyam Perugu, Assistant Professor, Department of Biotechnology, NIT Warangal, Telangana, and Chairperson of today's technical session, Dr. Sunil Ganatra sir, former Associate Professor, Department of Chemistry, Institute of Science, Nagpur. Session citation guest, Dr. Avinash Bharti, Head of the Department, Chemistry Department, Shri Ramdev Baba College of Engineering and Management, Nagpur. I welcome you all on behalf of Organizing Committee of ICNHTCS-2022. We are very fortunate to have us with an epitome of knowledge, Dr. Sunil Ganatra sir. I would like to take this opportunity to introduce today's chairperson, Dr. Sunil Ganatra sir. Dr. Sunil Ganatra sir is the former professor in Chemistry, Institute of Science, Nagpur. He is having around 29 years of teaching experience and 22 years of research experience. He did his PhD in 1999 and also have additional qualifications such as PG Diploma in Computer Science, BT Mumbai, PG Diploma in Industrial Management, VRC Nagpur, PG Diploma in Business Management, RTM Nagpur University, B.Ed from RTM Nagpur University. His area of interest are drug delivery, artificial intelligence in chemistry, natural product extraction. He has published more than 35 research articles in peer-reviewed journal, 10 in national conference and 2 in international conference. He is also having 1 patent published to his credit. He has also published 2 books. He has guided around 20 students for PhD, and out of it, 18 have been awarded and 2 are submitted. He has also been awarded and completed UGC-sponsored minor and major research projects. He also developed a biodiversity park at Fatri, Nagpur for MOIL, India. He is also having a research collaboration with School of Chemical Science, Pandit Ravi Shankar Shukla University, Nagpur. He is a recipient of B.N. Mankad Young Scientist Award, Chemical Society of India, 1992. Also a national level Person-Based Teacher Award, 2014 for Higher Education Innovation in Teaching. He is a life member of International Society for Computational Biology, USA, Indian Chemical Society, India, Chemical Research Society of India, IISc Bangalore. He has delivered more than 100 invited talks on computational chemistry, bioinformatics, and thermodynamics at various seminars, conferences, and workshops. He also worked as a coordinator for RUSA Committed Institute of Science, Nagpur, Committed for Autonomous Status Institute of Nagpur. He has also designed IT solution website for various government institutes. We are very much fortunate to have you with us, sir. With this brief introduction, I request Ganatra sir to give opening remark for this technical session. Sir, please.
Thank you. Good afternoon, everybody. And we are almost on the third sessions. And we had a very excellent lecture and the informative lecture from Satish Patil sir and chaired by the Atul Wankhede sir from BRC. Now we are entering into the one of the most talented scientists in India on the bioinformatics, and that is Dr. Perugu Shyam, who is presently working at the Department of Biotechnology at National Institute of Technology, Warangal, and in the capacity of assistant professor. He is expert in the bioinformatics and he has acquired PhD in the bioinformatics also. He has developed a number of databases also, and that is on nutritional atlas and nutrition. And more than 26 publications are there on international and national journals. And he has also supervisors, his PhD guide, and supervising one students. I've gone through his details and the papers and found that this is one of the most, he's one of the most talented person in India on the field of bioinformatics. And we are glad to hear from Dr. Perugu Shyam. And I request Dr. Perugu Shyam, please explore the knowledge to all youngsters on the bioinformatics and the possibilities of further research in this area. Please, sir, deliver your lecture, Dr. Perugu Shyam.
Thank you, sir. Thank you for the nice introduction, sir. So you are the foremost seniors for the in front of the seniors. I am the youngster delivering the lecture. So with respect, it's my pleasure to deliver a lecture on the current trends in the drug discovery and drug design. So first of all, I would like to thank the organizers for giving the opportunity for sharing my knowledge with the eminent experts and participants. So with this, I will start my presentation. My presentation is visible, madam?
Yes, sir. It is visible.
Thank you. So today I'm going to talk on the current trends in the drug discovery and drug design. So whenever we talk about the drug design and drug discovery, it's not easy to design and discover a drug. And today, if you thought, tomorrow the drug may not be produced. So, but there is a background, years of work together involved, and it also involved with the various domain experts. It starts with the chemistry, it starts with the biology, and it starts with the clinical researchers, as well as the toxicology studies, as well as the pharmaceuticals, right? So this, when you look at the preparation of the drugs, it also involves with the 4 phases, the phase 1, phase 2, phase 3, phase 4 studies. So each phase, as an average, it will take 2 to 4 years of the time. So whenever I am intended to bring one novel drug into a market, so it may take as an average 12 years to 15 years. So we don't know after the 15 years, when we do the lots of the research, we can spend the lakhs of the rupees or crores of the rupees and lots of the investments on the production of a drug and R&D. So we don't know whether the drug will work or the drug may be failure. So the drug may be accepted, approved by the IND and as well as the FDA, or that may be whatever we have submitted the reports and whatever the research background, whatever the clinical research, what is the human volunteers reports, which may documented reports which may submitted to the concerned authorities for the approval. So if they accept, the drug will come out and drug will be entered into the market. If they don't accept, or our results may not be satisfied, our results may not be shown the efficacy levels, or then the drug will be rejected. So whatever we have invested, manpower, money, and revenues, and other infrastructures will be. So that is a reason. So today, these are the traditional research which we have carried out. Today, the technology in front of us we are using the technology. So before going to do the laboratory experiments, we are designing a molecule. That molecules we are computationally checking. So we have a computational biology, we have a bioinformatics, and we have a cheminformatics approaches are available today. And today there are many softwares that are available to predict the molecular efficacy, affinity, and lipophilicity, and rule of phi, etc. So we'll go one by one. Yeah. So when our journey starts with the small molecular design. So that small molecular design, we can say that it is a ligand. So when you talk about the biology aspect, we can call it as the substrate. So enzyme and substrate. Enzyme is the receptor and substrate is the ligand. So whenever I say the ligand, so ligand is a chemical molecule or small molecule, so which donates a pair of electrons to the central metal atom or ion from the coordination of a complex. So whether it donates or it may be accepts. So whenever you have a word ligand, so the word ligand comes from the Latin word. So ligand can be an anion, or ligand can be a cation, or ligand can be a neutral molecules. So according to the ligands act as a Lewis basis. When I say the Lewis basis, it donates the electron pairs, and central metal atoms, that is viewed as Lewis acid, so that accepts the electrons. So the natural bonding between the metal to the ligand that varies in the covalent bonds or ionic bonds. Whenever we perform the molecular docking studies, the ligand has to go and bind with the receptor. So how it will bind? Based on the ionic bonds, based on the covalent bond, based on the hydrogen bonds, so based on the topological descriptors. So the topological descriptors we will discuss about when it comes to the QSR studies. So when I say the molecule, that molecule may come from the natural products, whether it is a plant sources, whether it is animal sources, whether it is a microorganism sources, or we may synthesize the molecule in a laboratory. So whatever we are designing in a laboratory, that we can call it as a synthetic compound. So the synthetic compound or synthetic substance refers to a substance that is man-made by synthesis rather than being produced naturally. So this is also refers to as a substance or compound that is formed under the human control or any chemical reaction, either by the chemical synthesis or biosynthesis, right? So now you look at here. So these are the chemical compounds which of one of my collaborator has synthesized in the laboratory. And these molecules which we have tested in the laboratory as a biological activities, such as the cell culture studies on the cancer, as well as we also tested the microbial studies. Then we have performed the molecular docking studies. Further, we have continued with the molecular dynamic studies. So in these molecules, so which molecule will act as a lead molecule? So which molecule will act as a lead hit molecules? We don't know. So until we perform a computational studies. So there may be R groups will be changed from the R1 to R2, R3 to R4. Then the orientation, the preferred orientation from the receptor. So when you perform the virtual screening, so then we came to know, so which molecule will go and bind properly and make the interactions with the receptor structure. Okay, so this we have published in the 2019. And now you look at here, whenever I say the molecule, so whenever I say the molecule, that molecule we require, so I have shown the small molecule, but I require the macromolecule, right? So then when I have a macromolecule, that macromolecule, we can call it as a receptor. So the receptor, we can call it as a druggable target. So the druggable target may be a protein, maybe DNA, maybe RNA, maybe your cell wall. So that we can call it as a druggable target. So that druggable targets are the receptors which our ligand molecule will go and binds to that. So then it will make the interactions, right? So this the proteins that are situated intracellularly are cell membrane. So that ligand, whatever the small molecule which we are expecting, so that will go and bind endogenously to the receptors, right? Ligands. So we have a two type of the binding modes. One type of the binding mode. So binding of a ligand to a receptor is reversible, and the degree of the functional response is proportional to the receptor structure. So now you can look at here. This is a general scenario which you might have seen in the test box. So you have a receptor, as I told you, receptor, and this receptor having a binding site or active site. So this is called allosteric site. So which molecule will come and binds to this active site, then it has to inhibit the activity of the particular receptor. So please note that this receptor structures has to be taken as a crystallized form. So which are the structures as designed by NMR or by a X-ray diffraction method. If these two methods are not in a position to design or develop a structure, then we can go for a computational method that is called homology modeling, comparative modeling, threading, and ab initio method. So once you have designed a molecule, then we identify the druggable targets or the binding regions and active sites. Then once you identify the binding regions, so based on that, you can design a small molecule. So that is designing of a small molecule. We can say that the pharmacophore hypothesis. So what should be there in my side chain? So the side chain where I should have placed the R1, what is the chemical compound, whether it is a CH3, whether it is a CH2, whether it is NO2, whether it is a SO2. So what we have to add. So based on the receptor structure, we have to design. So then that is called as a pharmacophore hypothesis. So for that, you need to synthesize the 1,000 molecules to 10,000 molecules. It depends upon. Once you synthesize the molecules, you need to do the virtual screening so that we can call it as whatever you have synthesized the molecules that we store in a library, that we can call it as a virtual library. So when you do the molecular docking studies, the virtual docking, so the one molecule will go and bind with the receptor. If it won't bind, then second molecule, third molecule, fourth molecule, fifth molecule, up to 10,000 molecules will be cross-verified. So whenever the strong affinity or lipophilicity are made good interactions, that will be given as a best rank or best molecules. So based on the ranking, so that ranking is a machine learning approach. So that machine learning approach will give you the search-based approaches based on the interactions. So that will be seen in the next. So we, in generally, basically how this phenomena works based on the biological inspiration. So we have in enzymes, we have an induced fit theory, we have a lock and key theory. In the lock and key theory, you have a lock. The respectable key only we can, whenever you have a suitable key you have, so then we can open the lock. So you can't open n number of keys. So whenever you have the induced fit theory, so you have a receptor, you have a ligand. So any one, either ligand has to change the orientation or receptor has to change the orientation. So which you are going to be a design that you need to decide it. That is called induced fit theory. So now you can look at here. So the structure orientation is like this. When it comes to here, the orientation is changing. So but in the lock and key theory, it won't change. So then when you are going to identify a target, so we need to identify the genomic biology from the human perspective. So what is the target? So if, for example, you have a COVID-19, but COVID-19, we know the target. So that is a spike protein. So in the spike protein, so what is the particular amino acids that are mutated? So then we, based on the mutations, wherever the amino acids are changing, so then based on that particular position, we need to design a drug. So, but similarly, we have more than hundreds of the diseases we have. So in that one diseases, whichever your targeted disease, from the targeted disease, which protein is responsible for the disease. Then once you isolate that protein and characterize the nature and identify the target, once you identify the target, then we need to design a small molecule, right? So the small molecule also we don't create a only single molecule. We will use to design, we use to synthesize the many molecules. That molecules we need to perform the molecular biology experiments, that is called, we used to create an n number of the essays. So that may be a blotting test, that may be autography test, that may be a cell cultures, that may be a antimicrobial studies, that may be a clinical trial studies, etc. So these small molecules from the interactions, from the high throughput screening studies, then we need to identify which molecule will show the efficacy, which molecule will inhibit the activity of a particular receptor. So based on that, so we can test from the computational studies. So one comes with the bioinformatics, another one comes with the cheminformatics approach. So this cheminformatics approach as a bioinformatics approach need to address the biological problem, right? So similarly, you have a biological structure. So biological structure will come up with the sequence, and sequence we use to convert into a three-dimensional structure. The protein modeling can be done and three-dimensional structure will be developed. So once you have a three-dimensional structure, so we need to identify the where the mutation is taking places. So where the active site is there. So based on the active site, we need to design the molecule. So once you design the molecule, then so we can conduct our computational studies. So further, if you wanted to know the molecular mimicking nature before docking and after docking, so that we can say the native molecules and complex molecules. So we wanted to perform the native as well as the complex molecular dynamic studies. So to understand the molecular mimicking nature, where in the which nanoseconds, in the which time interval, the molecule, our ligand is blocking the active site cavity. So we will come to the conclusions based on that studies. So there are the bottlenecks in the developing a functional relationships. So the structures are determined by the X-ray and NMR. The biological responses and biological processes like cell signaling, recognition, and interactions and chemistry, and these all are requires the molecular motions and time-dependent behavior. As I told, the molecular dynamics and simulations will facilitate the crucial role of the understanding of the nature. So as I told you, the scenario about you have a receptor and you have a small molecule. So this is a two-dimensional small molecule and this is a three-dimensional molecules. So whenever you have a small molecule, then we need to conduct the molecular docking studies. So this molecule will go and bind with this receptor, and where the molecule is bound with the receptor, then we need to identify where the interactions, which are the amino acids that are participated in the interactions. So that can be identified by using the various computational algorithms or various computational programs. So in another way, we can also create a dynamic libraries. There are the small molecular libraries or small molecular databases that are available on the website, data over the internet. So that also we can do the virtual screening. So then we can conduct the whatever the compound it has shown. So for example, you have 1,000 molecules. In the 1,000 molecules, maybe 5 to 10 molecules may show the strong activity with the receptor. So then similarly, we need to test the biological experiments on the cell culture studies. If it is a respectable cell lines are available. So based on the cell lines, you need to conduct the biological assays or protein assays or gene assays or HTS studies we need to conduct. So based on that, we can come to a conclusion. Then we can give so this particular compound will show the better affinity. So later we can conduct the animal studies. Once the animal studies also will be show the proper results, then that will be sent to a clinical trials. So this is the generalized scenario of the drug discovery. But why? we require the artificial intelligence. So the artificial intelligence requires the high resolution of the structural biology. So we have an organ, that is a human, that may be a tissue, that may consist of a cell, that may cell consist of a molecules, and molecule consists of an atom. So in the molecular dynamic studies and dynamic docking studies, as well as the dynamic studies or computational biology or bioinformatics studies, we will look into atomic stick positions. So we will able to find the interactions between the receptor as well as the ligand. So total ligand will go and bind to the total receptor. So it's only atoms, either oxygen, either hydrogen, either nitrogen, like that the interactions will be made. So the proper communication between the molecules is essential for the normal function of the cells. So that is the reason we need to understand determine the arrangement of the atoms. The atomic resolution is important in the structural biology with the crystallization of the receptor structures. So then the drug design is associated with the two stages. One is structure-based drug design. Another one is called ligand-based drug design. If you have a ligand, then so you need to design a structure-based, and you have a ligand is there, then we need to go for a ligand-based drug design. So these are the structure-based like design and structure-based drug design and ligand-based drug design. So this is about the traditional approach which we are following so far. So from the past 10 years, due to the technological developments in the computer science and information technology, as well as the chemistry and biology, so artificial intelligence is developed. So this artificial intelligence is overcoming the challenges that are identified, the novel interactions, so that are interfering with the small molecules versus the macromolecules. So we are utilizing the artificial intelligence to predict the consensus regions of the particular receptor side as well as the ligands. So how the artificial intelligence and machine learning approaches will predict the consensus regions and how they will identify the accurate molecules or hit molecules and that we may predict. So in the traditional versus the artificial approaches, the traditional knowledge which we have, it's only target driven. And whenever you are using the artificial intelligence, it is only whatever the data which we are providing, so it is based on the data driven. So traditional knowledge works well for the easily druggable targets that have a well-defined structure and whose interactions inside the cells are understood in detail. But when it comes to the artificial intelligence, we have algorithms that complex algorithms and machine learning can extract the meaningful information from the large sets of the data. You are provided the data, but for the artificial intelligence, you are providing the data. Based on the data, it will be go deep and it will make the training set and test sets, and it will classify the data and it will give the meaningful results. So when it comes to the traditional, so it is extremely limited due to the complex nature of the cellular interaction, because we have so many biological pathways, so many interactions, so many cell signaling mechanisms. So that is the reason we have a limited knowledge to intricate the cellular pathways. When it comes to the artificial intelligence, we can identify the small molecular compounds that could bind to the undruggable targets, such as proteins whose structures are not defined. Because we require the structure. Whenever you are going to do with the drug design and drug discovery study, we require a structure. So if there is no structure, we don't do anything. So we don't perform anything for the sequence. So you require a structure. So these artificial intelligence methods will start with the finding of a material consumables. Then based on that, we need to synthesize the molecule. Then we need to mine the data. So we have a small molecular databases, small molecular websites are there. So from the small molecule libraries, and we need to mine So which compounds are useful for the oncology, which compounds are useful for the diabetes, which molecules are useful for the Alzheimer's, which molecules are used for a COVID-19. Then we need to conduct the biological research, that is the target validation. Then from the target validation, then we need to find out the lead discovery. So once you identify the lead discovery, then we need to prepare a biomarker. So the biomarker discovery can be performed from the biology side. Then further we can conduct the experiments in animal studies. So there the preclinical, clinical studies can be conducted. Then we will give it to a pharmacovigilance. Then they will be fix up the dose of a particular molecule, and then the drug may be used the repurposing and repositioning. And we have explored the repurposing and repositioning during the COVID-19 situation, because we can't produce the drug in a 1 year or 2 years or 3 years. We require, when you are going to do the R&D based, so a novel drug you wanted to bring, so it requires the basic research, so that may take minimum 10 to 12 years of the time. So now you look at here, we have a target identification when you look at the machine learning approach. So the target identification can be done by the prioritization based on the gene disease associations or target, that is a druggable predictions, and identification of the alternative targets, which we have a splicing, splice variants and transcriptomes and other gene duplications, etc. So then based on these identifications, then we need to screen the chemical molecules, that is a small molecule and a ligand preparation. So that compound design with the desirable properties can be identified. Then need to synthesize the compound. The compound synthesis, they need to be planned accordingly. So which way the molecule has to be synthesized. Then we need to approach the ligand screening. Then we need to conduct the preclinical development and clinical studies. So when you have a different approaches, the applications of the artificial intelligence, the one will approach the drug discovery, the drug designing and drug screening. So drug designing can be done by the identification of a structure, and we can go for a drug protein interactions by the de novo drug design. So this is normal drug discovery. The screening can be done by basis on the biological activity prediction and toxicity prediction and physicochemical property prediction. So then pharmaceutical product development, the aid in the deciding the suitable expecient, and we need to monitor and modifying the development of a process. So then we can approach by the quality control and quality analysis, and clinical trials tests can be done, conducted. So we are using the artificial intelligence for the predicting the three-dimensional structure for the target identification, predicting the drug protein interactions, that is a receptor ligand interactions, and we are also determining the drug activity, and we are also designing the de novo drug design. So artificial intelligence is using in a polypharmacology, that is designing the biological specific drug molecules, that are also designing the multi-target drug molecules. So when you have a small molecule synthesis, that is a chemical molecule synthesis, the chemical synthesis is done in the prediction of a reaction yield. If you add some X, Y, Z chemicals, how much reaction can be yield? And that can be done in a artificial intelligence. So based on the data, so a artificial intelligence prediction of a retrosynthesis pathways, and it also developing the insights of into the reaction mechanisms and designing the synthetic routes. So it also uses the repositioning and repurposing, that is done by the identification of a therapeutic target, prediction of a new therapeutic use, and also used in the drug screening, that is a prediction toxicity, prediction of a bioactivity, prediction of a physiochemical property, and identification of a classification of target cells, etc. So the small molecules can be retrieved from the ChemEMBL or PubChem database or drug bank databases. So they may have more than 20,000 of compounds, and drug discovery can be identified by screening these molecules. So when you download the 20,000 molecules, we may identify only 20,200 molecules may have a lead molecule nature. Then we need to conduct the preclinical studies. From the preclinical studies, we may identify only 10 molecules. The 10 molecules, again, we need to go for a clinical trials. We need to test on the humans or human healthy volunteers. So from that, we can bring only one molecule. So that one molecule will enter into the market. So whereas the 20,000 compounds, when it comes to the one molecule. So whenever you have a computational data, so this data is available in an electronic form, then this 20,000 molecules which we train the system in the machine learning and artificial intelligence. So then we will conduct the predictive analytics. From the predictive analytics, so based on the R groups, based on the affinity, based on the acidity, based on the basicity, based on the lipophilicity, based on the number of the donors, number of the acceptors, number of the rotable bonds. So based on the constitutional descriptors, topological descriptors, everything will be fed into the data. So that machine learnings will perform the predictive analysis. Based on the predictive analysis, we will get the final molecules. So in the machine learning algorithm, as I told you, these are the SMILE molecules notation will be there. SMILES notations will be there, and the proteins or peptide bonds are available here. Then we can create a confusion matrix or multidimensional matrix. That multidimensional matrix will approach the mathematical descriptor. That mathematical descriptors will be generated. So once it is generated, then our future selection can be done easily. So then they leave one out or partial least squares will be fixed into the software. Then that will be predicted the drug molecules for the which can be used for a in silico analysis, or from the in silico analysis to the in vivo studies, right? So then you have two approaches in the machine learning as well as the artificial intelligence. We have a supervised learning as well as the unsupervised learning methods. So these supervised and unsupervised learnings is a normal scenario, so we can skip this. So from this, you have a preclinical studies, and we will conduct the many molecular profiling and imaging and microarray studies and HTS studies. And from this, we can disease category and the drug response can be identified. And the drug development can also be done by applying the model to the patients, which are polymorphic studies. We need to conduct the pharmacogenomic studies for the doing the research of drug development. So that polymorphic studies can be identified the single nucleotide polymorphisms and geographical locations and longitudes and latitudes and their ethnic behavior, and everything will be taken into considerations. Then based on the data, then we will test the different populations and different country peoples. Then based on the pharmacogenomics, our drugs will be analyzed. So there are the small molecules, that are small molecule libraries are available. So one is the drug bank, another one is the chem bank and PubChem and chem EMBL and zinc databases. These are the molecules. These are the databases holds these small molecules. There are the ChemSpider and other databases also there. Whenever you wanted to use, you can. So when exactly the molecular, the current scenario which we are approaching, so where we are going to conduct the QSR, COMFA studies, so there we are using the artificial intelligence as well as the machine learning studies, so which we are exactly applying so in the QSR study. So the molecular structure, the different compounds within a common mechanism of action. So that is a quantitative structure activity relationship. So you have 1,000 molecules or you have a 20,000 molecule. from the 20,000 molecules or the structures. So we wanted to assess the relationship, or we wanted to assess the activity of the 20,000 molecules. So then you need to conduct the biological activity. So the data of a small molecules or ligands data will be included into the study. Then based on the physiochemical properties, then we can identify. So these physiochemical studies will be conducted. So these will be depends upon the constitutional descriptors, topological descriptors, geometric descriptors, electronic descriptors, and physiochemical descriptors of a small molecule. It's not a large molecule. So constitutional descriptors, we will talk about the general properties of a molecular nature. The topological descriptors will calculate that done by the graph theory. Okay, so because the structure, whenever you are going to design a small molecule as well as a macro molecule, when you are going to do the molecular docking studies, molecular dynamic studies, we used to create a grid box. So the grid box is used to provide a space that is called topological space. That is developed by the graph theory, n-dimensional, n into n-dimensional box. So the geometric theory that is derived from a empirical schemes and encoded with the ability of the small molecule that participates in the different types of the interaction. So electronics, the electronics are referred to the electronic properties, that is van der Waals interactions, Coulombic interactions will be measured, and physiochemical properties define the behavior of the molecule that face the external reactions. So now you look at here, there are the open source softwares and cloud computing opportunity, cloud computing sources are available to store the data. So today, most of the databases or most of the servers are providing the space to store your molecules, whether it is macromolecules or small molecules, into their clouds. So then once you store the data, the databases will be store the data. And whenever you wanted to use that small molecules or macromolecules for your studies, then you can approach the machine learning approaches or deep learning studies called TensorFlow. So most of the advanced technology in the deep learning method, TensorFlow is the tool which we are using to come to a consensus of the significance to identify the particular molecular activity. So the TensorFlow is a very useful, and R programming we use it to use for the statistical analysis, regression, and correlation identification of a molecules. And the big pharma have enough data. So whenever you are going to develop this drug molecule or you are intended to bring the one drug molecule into a market, so you require the large number of the molecules data. So that is the data you may require from the Next Move software provides the data, and eTherapeutic also having a data, and benevolent artificial intelligence also data. So whenever you develop the molecules, whenever you identify the molecules that may get the patents. So today we are also using the natural language processing for developing the identification of a small molecules which are suitable to the particular target. So the chemist enhanced by the computational intelligence, that we can call it as a chemi-informatics studies. So whatever you are synthesizing the molecule here, the synthesized molecule will goes to the E-synthesis or Hemantica or IC synthesis. So then they will be used to sort out what is the purpose you are going to synthesize the compound, what compound you wanted to synthesize. Then based on that, we need to start synthesis, what compound, what chemical we required, and based on that, we do conduct the reaction mechanisms and we can synthesize the compound. So then, while doing that, any prediction errors will come. So the prediction and prediction errors will be identified again computationally. So then instructions will be given. So based on the instructions, which compound may be added, which temperature factor will be added, how much time you need to do the boiling, how much time, what solvent to be added to the, like that, the synthesis and reaction mechanisms will be goes on, and the computationally it will be predicted. So there are the advantages, there are the disadvantages with the any technology. So advantages with the integrating exchange with the experiences with the computers, as well as the theoretical, as well as the experimental peoples. So we require the critical analysis is needed for the theoretical studies. And if stupid errors comes, we need to stop. And there are the risks are associated with. So there are the complexity data will be generated, and we need to analyze thoroughly. Then, so humans' decision can be a loop, and the critical person, the person machine learning interface will be analyzed very fast because it's already trained data is available in the system. So machine learning as well as the artificial intelligence will be used in computational medicinal chemistry as well as the synthetic chemistry perspective. So artificial intelligence delivering on the back of the massive data sets, they turn the key high performance computing and also ubiquitous machine learning libraries. And we need to choose to build it, or we need to store the data. Then we need to buy the software and search engines or online resources or repositories we need to buy. So always there will be a challenges. The knowledge workers are more challenged by the artificial intelligence. So we need to use the integration and automation. And so there will be a organizational changes will be there. And so that is associated with the other computational approach. So there are the benefits by applying the artificial intelligence into a drug discovery and drug designing studies. So all does not rely on the predetermined targets for the drug discovery. So then artificial intelligence is the latest technology and advances in the biology as well as the computing technology. So this is developing a state-of-the-art algorithms for the drug discovery and drug development. So with the rapid developments in the artificial intelligence, so it increases in the processing of the power and reduction in the processing cost, because instead of doing all the experiments in the laboratory, we are computationally checking. So based on the computational predictions, so we will whether which direction or which path we have to move to synthesize the molecule to conduct the experiments. So it is reducing the cost of the experimental costs. And artificial intelligence has a higher predictive power to define the meaningful interactions in a drug design. And the potential for the false positives can be reduced by carefully designing the parameters in the essay of a question. So most importantly, the drug screening. So from the bench to virtual lab. So our chemistry scientists and chemistry researchers so use it to design the synthesize the molecules in the laboratory. But now we are moving into a virtual library, which we are going to design, which we are developing a molecules in a computationally. So that molecules we are testing computationally. Then after testing, then we are coming to the laboratory. Then we can synthesizing the molecules. So this is reducing the manpower and reducing the cost and giving some predictive or hypothetical ideas. So there are the drawbacks with any technology. So here also we have a drawback. The artificial intelligence, the case with any advance that brings the paradigm shift in our understandings of existing technology. Artificial intelligence still can't replace a human scientist entirely in the process of drug discovery. And whatever the predictions that comes from the artificial intelligence are as good as the algorithms used to investigate a data set. So the algorithm should clearly lay out the criteria that should be used to parse out a meaningful information when the results are in the gray zone of interpretation. So the predictions, whatever the predictions that are made by the artificial intelligence, the predictions made by the computers have to be verified by a researcher, by a scientist to make sure that they are valid. So because they are the prediction based approaches. So we are the original researchers knows the experience basis. Based on the experience, we can decide. So what is what. So with this, I will stop it here. So any questions that are welcome to the.
Thank you, Dr. Perugu Shyam. Any question from participants, please? Or you may put the question in the chat box so that we can throw it to the sir for further in descriptive answers for the questions. I'm very delighted to hear you, sir. It was an excellent and highly informative lecture on drug discovery, and probably you don't need to read a full book. You just go through your lecture and you learn everything, because you touch each and every part of this drug discovery, right from bioinformatics to the end of artificial intelligence, which is recently coming up. And you not only explained the process, but you also explained the experimental part, how it is to be done. Few points which I have gone through is that you explained the current trend in the drug discovery and drug discovery. You also explained the role of computational chemistry, chemoinformatics, genomics biology, and bioinformatics to prepare high throughput in silico process. You explained the biological structure of protein in 3D structure and in system dynamics. Also, you touched medicines and biology at the atomic scale, and then you entered to the artificial intelligence, the application of artificial intelligence, and how the machine learning approaches works in the drug discovery and the development. Also, you explain the public databases. This is very important. Generally, people don't know where are the data is available, and you explain the public repositories where people can get the list of the drugs molecules. And also, you touched down on the QSAR study, which was previously very well people used QSAR studies, but nowadays very less number of people are using this. But you also explained that how it can work out. And not only that, if you want to do the drug discovery on cloud, then how you can do that also explained by sir. Excellent lecture, and from my side, I think this is one of the complete book lecture, we can say that, and quite highly informative and very intelligently. All the slides are kept to inform you, to teach you, rather to say, for you to teach you how you can enter into the field of the drug discovery. Thank you very much, sir. And any questions from a participant, please throw it to the chat box. And I, with my thanks to sir, I now hand over to the organizer, please.
Thank you very much, sir. Thank you, Ganatra, sir. Thank you, Perugu, sir, for your wonderful lecture on current trends in drug discovery and design as a solution to various biological problems and its advancement in the artificial intelligence. It was a very informative and knowledgeable session, and I could read the same remarks in the chat box, but we don't have any question from the audience, from the participants, because it was a very explanatory, self-explanatory lecture, and it is very enlightening one. Thank you, sir. Now, I would like to invite Dr. Avinash Bharti, HOD Chemistry Department, Shri Ramdev Baba College of Engineering and Management, for citation of the certificates of Chair of the Session and Resource Person. Sir, please.
Good afternoon, all of you. It is really the excellent talk by Shyam Perugu, sir. Now I'm taking this privilege to cite this certificate. This is a certificate of appreciation and is proudly presented to Dr. Shyam Perugu for delivering an invited talk during the session of an international conference on New Horizons and Trends in Chemical Sciences, which is organized by Department of Chemistry, Dada, Ramchand, Bakhru, Sindhu Mahavidyalaya, Nagpur. and it in association with Indian Society of Analytical Scientists Nagpur chapter during 25th and 26th March 2022. Thank you. Now I request Shyam sir to kindly accept this certificate virtually.
Thank you, sir. Thank you for
Thank you,
your words, and thank you for providing the appreciation certificate, sir. Thank you, sir. Thank you, one and all.
Yes, sir.
Good afternoon, Ganatha sir.
Good afternoon, sir.
Thank you, sir. You nicely again briefed about this today's talk. And again, no doubt, sir explained each and everything. But the main thing is that the things which you explained. And thanks, sir, since you again told us about the use of computational chemistry and from the AI/ML to up to that bioinformatics, etc. Now, with this, I take this privilege to cite this certificate, sir. This certificate of appreciation and is proudly presented to Dr. Sunil H. Ganatra, sir, for chairing the technical session of an international conference on new horizons and trends in chemical sciences, which is organized by Department of Chemistry, Dada Ramchand, Bakhru, Sindhu, Mahavidyalaya, Nagpur, in association with ISS Nagpur chapter, and which is during 25th to 26th March 2022. Now I request Ganatra sir to kindly accept this certificate virtually. Thank you, sir.
Thank you, sir. Thank you very much. Thank you, Bharti sir. I find it as a pleasure and privilege to propose vote of thanks. I sincerely thank to the chairperson of the session, Dr. Ganatra sir, technical session speaker, Dr. Perugu sir, citation expert, Dr. Bharti sir, for kindly accepting our invitation and gracing this event with their presence. I am also very much thankful to the vibrant audience participants for their patient listening and active participation. I am sure that participants must have been benefited by attending this session. My thanks also goes to all people who gave their precious time in organizing this conference. I once again thank everyone and concludes that session is over. Thank you all.
Good afternoon, all. Now we are proceeding towards the fourth and the final technical session for today's function. Our guest speaker, Dr. Yoel Sasson, has already arrived, and Dr. Nankishore Karde has also presided, who is being the chairperson for today's session. Now I will formally hand over the proceedings of this formal session to Preeti Mangrulkar ma'am. Preeti Mangrulkar ma'am, are you there?
Yes, ma'am, I'm there.
Yes.
Am I audible, ma'am?
Please take over the session, ma'am. Thank you.
Yeah, thank you.
Yes, ma'am, you're audible.
Yeah, thank you. Good afternoon, everyone. On behalf of the organizing committee of ICNHTCS-2022, I, Dr. Preeti Mangrulkar, Assistant Professor at Sri Ramdev Baba College of Engineering and Management, welcome you all to this fourth session of this day 2 of the International Conference on New Horizon Trends in Chemical Sciences. The guest speaker for this session is Professor Yoel Sasson. He is an emeritus professor at Hebrew University of Jerusalem in the Department of Applied Chemistry. Dr. N.N. Karde, professor at Department of Chemistry from Rashtriya Sant Tukaroji Maharaj, Nagpur University, would be chairing this session. And Dr. Dahire, professor from DBSMV, would be citing the certificates to our guest speaker and session chair for this session. Before we proceed further, I would like to take this opportunity to introduce our session chair to all of you. Dr. N.N. Karde is a professor of organic chemistry and as well as head of the Department of Chemistry at Rashtriya Sant Tukaroji Maharaj, Nagpur University. He did his PhD in chemistry in January 2005. He has more than 21 years of teaching experience at postgraduate level. His areas of research interest include applications of hypervalent iodine reagents in organic synthesis, multi-component reactions for the synthesis of heterocyclic compounds, synthesis of natural products, cross-coupling reactions of iodinoleum salts. He has over 43 international publications in peer-reviewed SCI journals with an H index of 18 and I-10 index of 28. He has handled several major research projects as principal investigator, which includes 3 from DST, 2 from UGC, and 2 from URPS. He has guided nearly 9 PhD students for their doctoral research, and 4 students are currently working under his supervision. He has been a reviewer of several international journals of great repute, the Journal of Organic Chemistry, Advanced Synthesis and Catalysis, European Journal of Organic Chemistry, the Journal of Organic Chemistry, RSC Advances, amongst many others. He has been awarded with several fellowships and several awards. He has been a gold medalist for securing the highest marks in chemistry. We are really honored to have you, sir. And I would now request you to preside over the session and give your opening remarks and introduce our guest speaker for this session.
Good afternoon, everyone. Thank you very much, Preeti, for the introduction. Today, I feel very privileged and honored to chair this session of a very senior-most professor, Biosensor. Biosensor is a professor of applied chemistry at the Hebrew University of Jerusalem since 1976 and the incumbent of the Lester Aronberg Chair of Applied Chemistry. He served as visiting scientist and visiting professor at the University of Waterloo, Virginia Polytechnic Institute, the University of Paris Sud, the National University of Singapore, the Nanyang Technological University, and at the experimental station of DuPont. For 12 years, he held the post of Vice President of R&D at Magnesium Chemical Works, a global manufacturer of crop protection chemical society, today ADMA, in Beersheba. He also acted as consultant for other heading Israeli chemical companies. Through 2010 to 2013, Professor Sesson served as head of the Institute of Chemistry at the Hebrew University. During 2016 to 2019, Sesson acted as the director and CEO of SHARE, Singapore Hebrew University Alliance for Research and Enterprise. Professor Sesson is active in the area of green chemistry and environmental and process catalysis, photocatalysis, nanocatalysis, catalysis in energy conservation processes, including hydrogenation and transfer hydrogenation. He has published 270 articles and reviews over 50 patents in this field. Professor Sesson has coached 150 graduate students in their PhD and MSc thesis in applied chemistry. He is the founder of 6 startup companies: Clarion 2014, HydroX 2016, Aerovation Technology 2017, CatLife 2018, Plastic Bag 2019, and Celloflux 2020. So, dear friends, we are really having a senior most and experienced professor and a huge vast experience in the industrial area. The title of his talk is format bicarbonate cycle as a novel hydrogen and energy storage platform. So I request Professor Eol Session to start the lecture. Professor Sasson, I request you to make you unmute. Please make yourself unmute.
Sure. Okay, start again. Thank you very much for the kind invitation to talk to you, and for this very, very kind introduction. So I'm going to talk to you about energy, more specifically about energy storage, and more specifically using hydrogen as a mean to store energy and to utilize it in various energy needs. So the specific title is the format bicarbonate cycle, which is something that we have discovered, and I'm going to describe it to you now. And allow me to start with a quote from Jules Verne, the very well-known French author, that back in 1860, he stated that I believe that water will one day be employed as a fuel, that hydrogen and oxygen was constituted, used singly or together, will furnish an inexhaustible source of heat and light of an intensity of which coal is not capable. This is a very visionary statement, and as I'll show you, we are partially fulfilling it in this work. So let us start with a simple question. Why storage? We're talking about energy storage. Why do we need energy storage? The answer is that what we want to do is to adjust between the generation of power on the left and the demand for power on the right. Normally, they are not correlated, right? And at this point, what we need to do is to find a way to store the energy as we produce it and to release it when we need it. Now, this is not the case only for renewable energy. Although with renewable energy, it's more clear that when you convert wind energy and solar energy into power, there are a lot of differences between the daytime, the time of the year, and so on and so forth. So just to give you an example, this is the behavior of solar energy during day of the year, and we see the differences. And on the other side, we see the demand for power changing on a weekly basis on different users. So the solution is energy storage. Collect when available, deliver when needed. Now, interestingly, generation, we're talking now about the grid. Generation is growing 4 times faster than transmission. Why? Because transmission upgrade is very expensive, and normally it costs between 1 to 2 million per mile of building the grid. And on top of that, many millions for equipment. So typically, lines to remote area will what we mean is between tens and hundreds of miles. So it's becoming very, very expensive. This is why it is slower than the power generation units. And then we have to, as we said, we have to adjust the peaks of uses of power. What we see here is time of the day. On a normal day, on a hot day in New York area, and we see how it behaves. And the point is that grid must meet peak demand, not average. It must function under peak demand. And this is making the story quite complicated. And for that purpose, we are talking about storage. And the simplest way to perform storage nowadays is using batteries. Batteries, and what we see here is a huge, in Oman, a huge plant where you have all this large number of lithium-ion batteries. During daytime, they release the energy. During nighttime, where the need and the generation of power, the need for power is low, so I store the energy on nighttime and I release it on daytime, and in this way I shave the peaks, so to say. Now, lithium-ion batteries are very common, and they are used in numerous applications, including, as we know, in cars. Nonetheless, they have several disadvantages. It's the high plant cost, limited life cycle, operation and temperature degradation, recycling problem, practically volume limited, and there are numerous safety issues. So lithium-ion is a available solution, but it is definitely not the best solution. Two other options that I'll disclose to you here is what is called water pump. So you have extra energy at a given time. You pump water to an elevated place, keep it there, and when you need the energy, you release the water that are running the turbine and bring it back to you. So this is a very, very efficient method of storing energy by using pumping water to elevated areas. Another possibility is by compressing air. So when you have extra energy, you use compressor to compress air into a cavern underground normally. And when you want the energy back, you release it, and air will apply a turbine which will generate electricity back. Also, very, very efficient method. Normally, you can reach 90% yield of the energy that you store. However, what we are proposing, and we are not, of course, the only body that is advocating use of hydrogen. So we ask, why to use hydrogen as energy storage? And the answer is that, first, it's the highest energy per kilogram of all the fuels known. This is for hydrogen. It's the most common element, of course, in water. And it has zero emission upon application. When you use hydrogen as a fuel, zero emission, only water. And then, of course, you can produce hydrogen from water, or this would be called green hydrogen, or another alternative from natural gas. This is blue hydrogen. I'll explain it in a few minutes. Now, the advantage with hydrogen, beside avoiding pollution, and we have a slide here telling us that the EU air pollution is estimated in $1.6 trillion, which is 10% of the GDP all over. So avoiding air pollution is a critical issue, and using hydrogen definitely will be part of it. And for that purpose, two devices are very useful for the use of hydrogen as energy storage. This is the electrolyzer, where you convert electrical power into hydrogen by electrolysis of water. And the other part is fuel cell, where you have hydrogen, you want to convert it to electricity, you do it using a fuel cell. And indeed, if we look at this cartoon, the methodology for energy storage using hydrogen is already known. And what we see here is a typical house with solar energy and wind turbine. I use it to generate electricity, and I use electrolyzer to generate hydrogen. This hydrogen will have to be stored somewhere, somehow. And when I need the energy again, I will use this hydrogen to a fuel cell, which can then be used as electricity. So everything in this picture is known and available. The only missing point is the hydrogen storage. This is not solved yet. Just a very brief indication that battery storage versus hydrogen storage, we have to admit that battery storage is far more efficient, and normally it's between 70 to 90% efficiency, while in hydrogen storage, the efficiency is much lower. So there are some downsides to this issue. And this is the vision that people have put forward for futuristic world systems, where we have all kinds of different energies, including hydro, including biomass, and so on, all being combined into a system where hydrogen is the key common denominator between all these energy sources. Now, what is the problem with hydrogen? It is the volume it takes. Normally, if you want 5 kilograms of hydrogen for 500 kilometers, say, driving, you need 60,000 liters if you are at ambient pressure. So the solution here will be pressure. So you build tanks, and then you have another problem, which is cost and safety of using hydrogen. And typically, hydrogen volume at 1 atmosphere for 6-hour storage, 1 megawatt plant will need 2,200,000 liters. If you compress it to 900 atmospheres, you will need 2,400 liters. So it's actually a balance between volume and cost and safety. And this is a typical example. How do you transport hydrogen on the road? It's a very, very costly and problematic technique, normally under 200 atmosphere, and you deliver such a track, 400 kilograms of hydrogen. This is not economical, by the way. So other methods should be found. Again, this is a typical cartoon showing you what happened in a car. You want to ride on hydrogen, you need these high pressure vessels down in the bottom of the car. So we have that hydrogen is on one hand is cheap. Indeed, it is cheap, but to store it and transport it, make it expensive, where safety and pressure is the major concern. The solution, which we offer and others offer, is chemical liquid hydrogen carriers. And the idea is to take the hydrogen, to convert it into another compound, which is typically liquid, to transport it, and then to release the hydrogen again. So the key issue here is this hydrogen carrier. And the chemistry involved is to have some substance A, which will react with hydrogen to form another substance in a reversible way and store the hydrogen in this form here. And with this, we need to determine two factors: the free energy of the reaction, which determine the equilibrium, and the enthalpy of reaction, which determine the energy required to run the process. Both of them depend on temperature. And here are some examples of chemical hydrogen carriers. I will not go through them, but borohydride, very famous, hypophosphite, formic acid, ammonia, magnesium hydride, etc., etc. And normally what we want from a good hydrogen storage system is we want high gravimetric volumetric hydrogen storage capacity, thermodynamic stability, good kinetics of hydrogen release and generation, reversibility of the storage, low energy consumption, and then thermal conductivity, and of course. And here are some examples of what is called liquid organic hydrogen carriers. This is not our solution yet. And we see numerous hydrocarbons, which are either saturated on the left or dehydrogenated on the right. And in this way, you store hydrogen in these compounds here. And when you release the hydrogen, you get these materials. And this is very well known and now being handled by several companies. Another demonstration here of the process of hydrogenation, dehydrogenation of several of these carriers. And the most famous one, and almost the most useful one, is the one we see here. This is a reaction where I take toluene with hydrogen to generate methyl cyclohexane. Here we are. The hydrogen is stored in this material. Now, the backward reaction, I release the hydrogen. So the methyl cyclohexane will release the hydrogen and generate again the toluene, which I can recycle. This is a very interesting concept, but one thing we need to keep in mind, see that the delta H, the enthalpy of this reaction, it's very, very exothermic going to the right and endothermic going to the left. This means that I will need a significant amount of energy to run this reaction. Nonetheless, I'll skip this. A company, a Japanese company called Chiyoda Corporation, have introduced on commercial level their concept of hydrogen storage and transport. And this is how it works. I have the hydrogen, which I release in various methods. I store it after hydrogenation in this molecule using this. I hydrogenate the toluene here in this reactor here. I store it and then transport it when convenient overseas to any distance on ground or on ships. I reach the destination, storage, and then I release it in dehydrogenation and I get the hydrogen there. So full cycle. And Chiyoda already built a commercial process where they take this hydrogen carrier for a distance of 5,000 kilometers from Brunei near in Borneo, all the way to Japan, to Kawasaki, 5,000 kilometers using ships. This is already applied commercially. And their vision on the way is far more than that.
अच्छा यहाँ का स्टूडेंट एक PhD कर रहा है.
No, please unmute yourself. Please unmute yourself. Don't disturb.
So what we see here is the vision of Chiyoda, how toluene will be used all over the areas, different areas, to supply hydrogen to remote areas. And we see how two kinds of hydrogen which you produce by electricity, which, as we said, this is the green hydrogen, or hydrogen that you produce from natural gas. This is called blue hydrogen because the CO2 formed is being charged underground and kept there. So this is a very, very visionary picture that we see here. And I believe it has indeed a great future. And on top of that, look at this. These companies, together with Chiyoda, had decided to build in Rotterdam, in Holland, a terminal where the hydrogen will be transferred from Singapore or from the Far East to Holland via transportation on ships. And calculations show this is much cheaper than the methodologies that is being used today. All right, so let's now switch to the solution we are offering. And this is the formate bicarbonate cycle that we have developed. And what we see here is that this is our hydrogen carrier. This is a salt of formic acid. It's called potassium formate. And in the presence of certain catalysts and water, remember that water is part of the source of hydrogen. So one atom of hydrogen coming from water. So the reaction between water and bicarbonate and formate will release hydrogen and will produce potassium bicarbonate. And the reaction is reversible. This is the major point here. And the reaction backwards would be hydrogen with potassium bicarbonate to form water and potassium formate again. So you can reuse it. So this is the formate bicarbonate cycle. And when I consider potassium formate, it is non-corrosive and non-toxic. It is used as de-icer today. It's the most water-soluble salt known of all the salts, 770 grams per 100 ml. Amazing. It's indefinitely stable in solid state and in aqueous solution, and it rapidly and selectively decomposes to hydrogen in presence of a catalyst. And the point is that minimal energy is needed per cycle. Again, the same advantages, and see how it looks. Very, very safe. I can drink it, by the way. It's non-toxic, and you can keep it in plastic vessels. Now, here, this is the reaction, the reversible reaction. This is the equilibrium constant, but most important, the free energy and the enthalpy, close to zero in both cases, indicate that the reaction is very reversible. It's almost the same. You can go from here to here just by switching the pressure, a little pressure of the hydrogen. And on top of that, the energy you consume for this transformation is minimal, 0.5 kilocalorie per mole, very, very low. And this is the overall vision, where this is the grid, this is the load, and on the way, I build a system where I can store the energy and release it when I want. I have format solution storage, I have bicarbonate solution storage, I have the electrolyzer, and I have the fuel cell. This is the same, describing the process in more detail. It's we built it and calculated it, and it's a very, very useful cycle. So the most important issue now, when I compare different techniques, including Chiyoda technique, in terms of the energy you need for the process. In Chiyoda, you need a lot of energy for the process. Normally, energy consumption to store 1 kilogram of hydrogen in kilowatt hour. In the case of Chiyoda, it's 12.5 kilowatt hour. So the energy you have altogether in hydrogen is about 16 in kilogram of hydrogen, about 16 kilowatt hour. So most of it you waste on the process. So Chiyoda have left only with 3.5 kilowatt hour per cycle, per 1 kilogram hydrogen. While our process, the format bicarbonate cycle, it will be somewhere between 16 to 14 kilowatt hour left, net energy left in the process. So this is very, very unique and obviously advantage over Chiyoda, which is already proven as a commercial technology. Okay, so very briefly, I'll go through the density, the advantages of our systems, and we have here the issue of density. So this is our system here versus other methodologies, and then the flammability and toxicity. We are here, while other methods are all high to the right, and then the pressure and temperature you need. We are here, much lower than other methods, and the pressure you need for loading, we also here very low compared to other methodologies. So there are numerous advantages. And when I try to figure out the mechanism, it looks like this. The catalyst is palladium, and on the surface of the palladium, the process takes place. Classical chemical bond formation and bond breaking, going from formate and water to hydrogen and bicarbonate and backwards. So typically, most important figures in catalysis in general is the turnover number, which are number of mole of product versus mole of catalyst, and turnover frequency, mole of product per mole of catalyst per time. And both these figures are very high in the catalytic system we have developed. And this is a very simple and easy to follow methodology for quantitative kinetic measurement, and see the our reaction is taking place here. You inject the formate solution, then you have this trap to measure the volume of hydrogen being released, and simply to wait, and then to calculate the rate of the process. This is for the hydrogen release, and this is for the hydrogen charge under pressure. Again, follow this time following the pressure change with time, so you can follow the kinetics. Okay, so just a demo of the process in charging and in releasing and in catalyst treatment. So the overall is being done this way. And what we see here is that multi-cycle of charge and release that we carry over 25 times back and forth to release hydrogen and to charge it again, and end up with a process that can be applied on larger scale. And at this point, I thank you for your attention, and I'm, of course, open to comments and questions. Thank you.
Yeah, thanks a lot, sir, for a very interesting talk. The forum is now open for discussion. I would request all the participants to post their questions on the chat so that we can take up their questions. I think there are no questions. I would request Dr. Karde to give his concluding remarks on the talk.
Excuse me, ma'am.
Yeah. Yes, please.
There is one participant of ours, Megha Karsh. I think she wants to raise a question.
Yeah, please go ahead.
Thank you so much for wonderful session. Sir, my question is, before the second last slide, you have shown the pressure which is maintained is 10 atmosphere and temperature is around 35 degrees Celsius. So how this temperature is maintained? Is it easy to maintain this temperature everywhere?
Well, the system is with open hydrogen source.
Okay.
So when the hydrogen is consumed, another amount is coming in. Okay, understood?
Yes, sir. Yes. Thank you so much.
Okay, thank you.
Any other questions from the participants? You may raise your hands or you may post your question on the chat box. Okay. If there are no more questions, then I would request Dr. Karde to give his concluding remarks on the talk.
Yes. We have listened a very useful and informative lecture of Professor Yol Sasson. His lecture was all about related to the hydrogen as a green fuel. It is a very demanding kind of category of fuel because of zero emissions. Therefore, many problems of air pollution can be prevented. This electrolysis of water to generate hydrogen and oxygen is definitely one of the methodology to prepare the hydrogen. But there are again a lot of issues as far as the cost of its production is concerned. Professor Yawal has also focused on certain data where there is a lot of concern about the storage of hydrogen gas, because it is a very costly kind of affair, and safety measures are also concerned there. This work is what I want to say is correlated with the another literature report, or I would like to say one of the plant already established in Japan that was related to the hydrogenation and dehydrogenation of toluene. But this dehydrogenation of and therefore even though that plant is there, the present work looks to be a very alternative to that one. If you consider this hydrogenation of toluene and again the reverse process, the dehydrogenation of hydrogenated toluene, it's a very endothermic process. It is associated with a lot of energy issues. So compared to this, the present work, listen to Professor, is about the format and bicarbonate catalytic cycle. It is indeed a very excellent method as far as this overall production of hydrogen gas is concerned. This potassium format is a raw material for this one, which is very non-corrosive. This is non-toxic. It is inexpensive. And moreover, the energy required here for this overall process is very small compared to the hydrogenation and dehydrogenation of toluene. Really, I'm very much motivated to again read more literature about this one. Your lecture was indeed very inspiring, motivating, and very useful to all the audience here. So thank you very much, sir.
Thank you
for this excellent talk. Over to Preeti.
Thank you, sir. Now I would like to request Dr. Sunil Dahire, who is a professor at Dada Ramchand Bakhru Sindhu Mahavidyalaya, Nagpur, to cite the certificates as a token of appreciation for our guest speaker as well as for our session chair.
Thank you, ma'am. Respected Dr. Eul Sesson, Lester Aronbach Professor Kasali, Institute of Applied Chemistry, the Hebrew University of Jerusalem, Israel, and Dr. Nandakishore Karde, Professor, Head, Department of Chemistry, RTM Nagpur University, Nagpur. I, Dr. Sunil Dahire, Professor, Department of Chemistry, Dada Ramchand, Bakhru, Sindhu Mahavidyalaya, Nagpur, thank both of you for accepting our invitation and for gracing the technical session with your presence. I hereby hand over the certificate of appreciation to Dr. Eul Sesson for certificate of appreciation is proudly presented to Dr. Eul Sesson for delivering an invited talk during the technical session of International Conference on New Horizons and Trends in Chemical Sciences organized by Department of Chemistry, Dada Ramchand, Bakhru, Sindhu Mahavidyalaya, Nagpur, in association with Indian Society of Analytical Scientists, Nagpur chapter, during 25th and 26th March 2022. I am presenting the certificate of appreciation to Dr. Nandakishore Karde sir for certificate of appreciation is proudly presented to Dr. N.N. Karde for chairing the technical session of an international conference on New Horizons and Trends in Chemical Sciences organized by Department of Chemistry, Dada Ramchand, Bakhru, Sindhu Mahavidyalaya, Nagpur, in association with Indian Society of Analytical Scientists, Nagpur chapter, during 25th, 26th March 2022. Our sincere gratitude to both of you, sir, for bearing here with us. Thank you.
Thank you.
Thank you so much, sir. I would like to take this opportunity to thank Professor Eul Sesson for his excellent talk and for gracing this conference with his presence. Thank you, sir. It was wonderful to hear to your talk. I would also like to thank Saurav Chakravarti, who is a doctoral scholar at Kasali Center for Applied Chemistry, Hebrew University, Jerusalem, for his kind cooperation in coordinating with the organizing committee and helping us to organize this lecture of Professor Eul Sesson. I would also like to express my sincere gratitude towards Dr. Karde for efficiently chairing the session and giving his valuable time. I would also like to thank Dr. Dahire for citing the certificates. And last but certainly not the least, I would like to thank all the participants for their patient listening and active participation. With this, I would like to conclude this session. The valedictory session is at 3 p.m. and I request you all to join us for the valedictory session. Thank you so much.
Thank you.
Thank you.